Hello, thanks for coming to the last day of this PLDI 2024-5. Yeah, and we will have a lot of rain today, so please keep inside. I will just briefly introduce today's schedule. Before we introduce today's schedule, we already thanks to our sponsors, especially the Apple, Amazon Web Service, and the Huawei. And we don't have some special schedule today, but we have a URM launch today. So please go to the Lilac room if you want to attend the URM launch. Yeah, thanks for the coming today again, and I give my mic to Zach. Yeah, thank you.
Okay, folks, today we have another treat especial. I feel like the keynotes have all been fantastic. So Ishel's going to be giving the final keynote here at PLDI. I remember I first learned of Ishel when she was giving a job talk at UC San Diego, and there's a whole thing about abduction. And I thought it was some kind of like exercise or something for your core. And today we're learning about another fancy word, neurosymbolic reasoning. I feel like every time Ishel gives a talk, I walk away feeling very enlightened. So building on the stuff we learned from Sunho yesterday, I think we're in for a real treat. Ishel is, as you all saw, won the Reynolds Research Award last night, has been a true guiding light in the community, not just incredibly productive in research, but her students have all gone on to do amazing things. So I think just across the board, a fantastic member of the community. So Ishel, please take it away.
Thank you so much, Zach. Thanks, everyone. It's a great pleasure to be here. So as Zach said, my name is Ishel Dillig. I'm a professor at UT Austin, where I'm very fortunate to lead a wonderful research group called Utopia. And today, I'm going to tell you about some of the work that we've been doing on the topic of neurosymbolic program synthesis. And I'll try to highlight in this talk how this field can help bridge perception and reasoning for many real-world applications. So first of all, to set the stage for this talk, I want to quickly go over two different learning paradigms that have emerged over the last several decades. So as you all know, one of these learning paradigms is, of course, deep learning, which has had a profound influence on computer vision and natural language processing, as well as many other areas outside of computer science recently, for example, in the natural sciences. Oops, sorry. This does not seem to be working. All right, let's see. Let me retry this. Give me 1 second. All right. Hopefully that won't happen again. I don't know what happened. Okay. But there's also another learning paradigm that has received an enormous amount of attention in the programming languages community, and this is, of course, program synthesis. And the goal of program synthesis is to automatically generate programs from some high-level expression of user intent. For example, it could be input-output examples, or it could be logical specifications. And program synthesis, as many of you know, has found numerous applications in the context of software engineering, data science, spreadsheet automation, and so on. Now, I would argue that despite the different use cases of these methods, deep learning and program synthesis are actually in some ways very complementary to one another. So in particular, if you think about the strengths of deep learning and deep neural networks, I would argue that where they really shine is their flexibility and their ability to handle messy, ambiguous real-world data like videos, images, and so on. On the other hand, if you think about their shortcomings, they tend to be fairly data hungry, right? They typically require large amounts of labeled input in order to learn something useful. And perhaps even more importantly, they're not very interpretable, right? It's very difficult to stare at the weights of a trained neural network and say, aha, I know exactly what this network has actually learned. And on a related note, not only are they uninterpretable, but they also turn out to be extremely difficult to verify despite several attempts from this community. It's not, verification doesn't scale, and it's very difficult to prove properties about deep neural networks. On the other hand, if we think about programmatic representations and program synthesis, we see a very different profile. So I would say that their biggest advantage is interpretability. So it's much easier to inspect a program and understand what it is doing. And also on a related note, they're also much easier to verify thanks to decades of research in the formal methods and programming languages communities. And I would also argue that a lot of recent research in programming languages has shown that it's possible to learn programmatic representations in a way that's not very, very data hungry. On the other hand, in terms of their weaknesses, programmatic representations and program synthesis is not very good at dealing with ambiguous, messy data. So this brings me to the central question of this talk, which is how do we combine these two learning paradigms into a unified approach that can tackle real-world problems much more effectively than either approach can on their own. So this is precisely the point of neurosymbolic learning. So the idea here is we want to try to get the best of both worlds by using neural components for perception or perception-like tasks. But at the same time, we would like to combine them with programmatic representations in order to do better logical reasoning and algorithmic manipulation. And in a nutshell, by using neural components, we get the ability to handle complex unstructured inputs, but at the same time, by combining them with programmatic representations, we get composability, we get modularity, and importantly, we also get greater interpretability as well as more data-efficient learning. Okay. So with that background, here's a quick outline for the rest of the talk. So this talk roughly has 5 segments. So in the first part, I'm going to introduce the general neurosymbolic learning framework that both my group and several others have been advocating for. And then in the next part, we're going to look at different instantiations of this framework for several real-world applications. One of them is going to involve images, namely image search and editing. Then we're going to take a look at an application that involves text. We're going to talk about data extraction. And I'm also briefly going to talk about an application in robotics. And then in the final part of the talk, I'll tell you about some ongoing work that we have on ensuring trust in the neurosymbolic setting. Okay, so first, let's start with the general neurosymbolic learning framework. So in my view, whenever we talk about a learning framework, there are 2 important questions that we need to answer. And the first question is, what is the representation? In other words, what is the thing, the shape of the thing that we're actually trying to learn? And then once we settle on the representation, there's the equally important question of what is our learning algorithm? What are the methods that we use in order to learn this desired representation? So let's briefly talk about both in the context of neurosymbolic program synthesis. So as its name indicates, the representation here is going to, of course, blend neural networks with symbolic traditional programming language constructs. And in more detail, the representation is typically going to be a program that's expressed in a domain-specific language rather than often a general purpose language. And you typically choose a DSL in order to achieve a good trade-off between expressiveness within that domain, but also being amenable to few-shot learning. Okay. All right, so since our DSL is neurosymbolic, of course, it's going to have some neural primitives. And as I was saying earlier, these neural primitives are often going to be used for perception. And for the purposes of this talk, all of these neural primitives are going to correspond to pre-trained neural networks. Okay? So for example, to be concrete, if we have a domain-specific language where the input is images, Here you might have neural primitives that are used for doing things like image segmentation or object classification. And ultimately, these neural primitives allow us to take some raw set of pixels, a raw image, and then allow us to parse it to a more symbolic representation like a scene graph, where you have a notion of objects and where each object has various attributes associated with it. So for example, like you have an object type, that's a face, it has a certain ID, and various attributes like whether it's smiling or not, and so on. So in general, these neural primitives in our language will be crucial for taking some high-dimensional unstructured inputs and parsing it to a symbolic representation that is amenable to programmatic manipulation. Now, of course, since we're dealing with programming languages, we're also, of course, going to have more traditional programming language constructs like conditionals, loops, as well as several task-specific abstractions, for instance, fold or filter. And importantly, I do want to note that we don't prescribe any particular programming paradigm here. Our DSL could be imperative, it could be functional, or it could be declarative. And in fact, in the rest of the talk, when we look at applications, you'll see all of these three different paradigms come up in different domains. Now, another point that I want to make here is that in terms of their syntax, the symbolic constructs and the neural components pretty much look, exactly the same. They often both look like just regular function calls. But in terms of their semantics, there is an important distinction. So in particular, the symbolic constructs have precisely defined semantics. So we know exactly what they do. They always produce the ground truth answer. On the other hand, the neural components, we don't know what their semantics are. They're like black boxes to us. And furthermore, as you will see later, which will play an important role, they can also have mispredictions. They don't always produce the ground truth answer. So we briefly talked about the representation. Now let's talk about the learning algorithms that we use in this context. So first, what are the goals of our learning algorithm? I would say that there are two important goals that we want to achieve here, and one of them is data efficiency, meaning that we would like to learn the desired program from very small amounts of user input. And this is important because in program synthesis, we typically want to customize a program for an individual user. And of course, it's not really realistic to expect them to provide a ton of labeled data because it's coming from just a single person. And this is precisely going back to what I was saying earlier. This is precisely why we typically deal with domain-specific languages here as opposed to general-purpose languages, because by having this DSL, we can essentially bake in sufficient inductive bias into the hypothesis space that in turn facilitates few-shot learning. Now, in addition to data efficiency, another important goal is that learning should be fast. And again, this is important because program synthesis is often used in interactive user-facing contexts. And in this context, of course, users don't want to wait for hours and often not even for minutes. Okay? So in order to achieve this goal, as you will see, we're going to be leveraging the formal semantics of our programming languages, at least of the symbolic constructs, in order to facilitate efficient learning. All right, so this brings me to an important point that I wanted to make about the learning algorithm. So recall that we have this representation that blends neural networks with symbolic constructs. And just like the representation, often the learning algorithms that we use also have this interplay between neural guidance and symbolic reasoning. And what do I mean by that? Well, at the core, program synthesis is a search problem. So at the core, we have some sort of backtracking search algorithm. But rather than doing blind search, we are going to be using various kinds of machine learning models, including LLMs, in order to guide the search for plausible programs based on the limited training data that we have. But equally importantly, we're going to leverage logical reasoning and program analysis in order to systematically prune large parts of the search space. As you will see, we will resort to techniques like a static type system or abstract interpretation in order to prove unrealizability of entire parts of our search space. So that was a quick overview of the learning framework. Now let's look at some concrete instantiations of this framework. And to get us started, I'm going to first talk about our work on image search and editing. And if you're interested and would like to learn more, this segment of the talk is based on our PLDI paper from 2 years ago, as well as some follow-up work at Chi-24. And this work was led by my student Celeste Barnaby. So let me give you a motivating scenario for what we're trying to do here. So let's say you have a large collection of images, and some of these images are relevant to what you're looking for, and others are not. So you want to search for the relevant subset of the images, and maybe for those that are relevant, you may also want to apply some selective edits. Okay, so concrete example. So let's say you have a bunch of photos from your childhood, and for whatever reason, you want to find all the images that contain two of your friends sitting next to one another. Let's say these are Michelle and Greg. Let's say this is Michelle and this is Greg. And so that's the search aspect of the task. You want to find all the images where Michelle and Greg are next to each other in the image. And maybe also for privacy reasons, you may also want to edit this image. For example, you might want to blur the faces of everyone else except for your friends Michelle and Greg. So for instance, if this is our input image, we want to obtain this output, and we want to apply a similar transformation to all of the images in your collection. So I would contend that this kind of task is a perfect fit for neurosymbolic learning for a variety of reasons. So the first reason is that obviously there is a big need for using neural networks here because we need to do perception. We need to do facial recognition. We need to be able to answer the question, does this face belong to Michelle? Does this belong to Greg? And so on. But beyond just doing facial recognition, there is also some sort of basic logical reasoning aspect to this task. Namely, after detecting the faces, you need to reason about the spatial relationship between these objects. And for example, you want to answer the question, are these two objects adjacent to one another in the image? And last but not least, there's also, of course, a programmatic manipulation aspect to this task. Once you detect all the faces, you want to iterate over all of them, and you want to apply an action, in this case blur, to all the faces except for two specific people. Okay. So for these reasons, we took a neurosymbolic approach to these kinds of image search and editing tasks. And as usual, our starting point was to design a suitable domain-specific language. So you don't have to understand everything that's going on here, but at a high level, programs in this DSL allow us to extract a set of objects in the image using this non-terminal E, which I'm going to refer to as object extractor. And then you can apply various actions like blur, blackout, sharpen, and so on. Okay? And if you look at this non-terminal E for object extraction, one thing that I want to highlight here is we have a mix of symbolic constructs as well as neural components. So in particular, these constructs like complement, union, and so on are just, they have precisely defined semantics. They just correspond to regular set operations. On the other hand, we also have these constructs like find and filter, which do what you might expect them to do. But importantly, these predicates that are nested inside them are actually implemented using neural networks. So for example, you have a predicate face of n that's allowing us to do facial recognition where n is some identifier of a specific person, and object of O is doing object classification where O could be something like a face or a cat or a dog and so on, a certain type of object. Okay? And if we go back to our running example from earlier, this is how you may be able to express this task in our DSL. So basically, if you look at this highlighted part, this is extracting the part of the image that contain Michelle and Greg, but only if they are sitting next to one another. So in more detail, this find, the first instance of find, is extracting Michelle, but only if she's sitting next to Greg. And similarly, this one is doing the symmetric thing, but for Greg instead of Michelle, and then we take their union. And then what we do here is we take the complement of that region and intersect it with all of the faces, which ends up giving us all the faces except for Michelle and Greg. And finally, we can apply a specific action like blur, which gives us the desired output image. Okay. So that was a quick overview of our representation in this context. Now let's talk about the learning task and the learning algorithm. So here, in order to automate these image search and editing tasks, we take a standard programming by example approach. So the idea here is that the user provides a small number of labeled examples, so a few input images, and by few I mean hopefully less than 5, and also their corresponding output, whether that image is relevant, and if so, what is the desired edit. And then our goal here is to learn a program in this DSL that can be used to perform the desired task. So the question is, how do we do this in a way that is actually effective in practice? So for those of you who may not be familiar with program synthesis, before I talk about the specific ideas used in our method, I want to give a very brief background on program synthesis techniques. And first of all, there are many different program synthesis techniques, but one common algorithm is what people refer to as top-down enumerative search. So the idea here is that you have the notion of a partial program, and you can think of a partial program as an abstract syntax tree, where some nodes in this abstract syntax tree are annotated with concrete terminals in the grammar, like union, intersect, and so on. But some of the other nodes are annotated with non-terminals, meaning that they're currently unknown, and they can be instantiated with arbitrary expressions as the search progresses. Okay, I'm going to often refer to these unknowns as holes in the partial program. So the idea behind top-down enumerative search is that at every step you have a work list of these partial programs, and then at every step you dequeue some partial program in your work list. You can either do this using a heuristic like selecting the simplest program, or often you can also use some sort of machine learning guidance to do this. But in any case, you get a program, and then you choose one of these holes in the program, and you instantiate it, you expand it using the productions in the grammar, and you keep doing this until one of two things happens. So one possibility is that you have a complete program that's actually consistent with the user's specification, and if that happens, you often produce this as the output of the synthesis procedure. But in some cases, you may still have a partial program, but using various techniques, you can actually prove that this partial program is inconsistent with the specification. What I mean by that is you can construct a proof that there is no completion of this partial program that's going to satisfy the specification. So in that case, we refer to that program as infeasible or unrealizable. So a big part of program synthesis deals with the question, how do you detect these infeasible partial programs as early as possible within the search procedure? So this is precisely where the semantics, the formal semantics comes into play. And the idea here is that we would like to leverage the semantics of the symbolic constructs in the DSL in order to perform logical inference and prove unrealizability of certain parts of the search space. So let me just illustrate that with a concrete example in our image domain. So let's say that we're considering this partial program for the object extractor, where we committed to union being the top-level construct, but the operands of union are currently unknown. Okay, so that's indicated by these question marks. Now, also suppose that in the examples that are provided by the user, they're applying a blur action, but this blur action is only applied to faces, right? And even though there are many other types of objects in the image. Now, from the semantics of union, we know that it's going to preserve whatever object is extracted using its operands. So based on that, we can deductively infer that however we instantiate these holes, they must also only produce faces. If they produce something other than a face, then we know we must be on the wrong track, right? So therefore, if at any point we instantiate this hole with something like is cat that basically extracts all the cat objects, we know we are on the wrong path, and we can prune this partial program without even considering how to instantiate the second argument. So this is the idea behind how you use the formal semantics to do systematic pruning of the search space. Now, another important idea here is based on the observation that our hypothesis space is highly redundant. So what I mean by that is there are many programs in our hypothesis space that are actually observationally equivalent, at least on the examples provided by the user. Okay, and we would like to eliminate redundant parts of the search space and do some sort of symmetry breaking, if you will. So to illustrate what I mean by that, again, let me give a concrete example. So let's say we have this partial or complete program where we take the union of some expression E with all of the objects that have their eyes closed. This basically gives you all the faces where the people's eyes are closed. But now suppose that in the examples provided by the user, there are no faces that have their eyes closed, right? So in other words, this is just going to give us the empty set. And if you take the union of E with the empty set, well, that's obviously going to be observationally equivalent to whatever E produces. And since this entire partial program is equivalent to something much simpler that we likely explored before, there's no point in considering this duplicate program. So based on this, what our method does is that it uses a combination of partial evaluation and equational term rewriting to eliminate redundant parts of the search space. So that's all I wanted to say about the learning technique, and now let me give you some highlights from our evaluation. So we implemented this method in a tool that my student named ImageEye, and we used it to automate a diverse set of image editing tasks involving different type of photographs. And just to give you some idea, for example, we have this set of photos from a wedding, and you might want to, let's say, search only those photos that contain just the bride and the groom and no one else. And similarly, you may want, if you're given a bunch of photos of receipts, you may want to remove sensitive information, for example, phone numbers or credit card numbers and so on. So just to give you some ideas about the tasks. And what we found experimentally is that our tool was able to learn the desired program for 96% of these tasks, given a 2-minute time limit for synthesis. And furthermore, we found that it's quite data efficient. It requires 4 examples on average. So we think it's not too burdensome on the user. And also in terms of the efficiency of synthesis, we found that it's practical enough to be used in interactive settings with a median learning time of around 1 second. Okay. So to recap, in this segment of the talk, we looked at an application of neurosymbolic programming in image search and editing. And by using neural components, we get the ability to do things like facial recognition, object classification, and so on. But at the same time, by combining these neural networks with programming language constructs, we get the ability to do some sort of logical reasoning over the detected objects and also programmatically manipulate images. Okay, so in this next application domain, I'm going to switch gears to a different modality of input, namely unstructured or at least semi-structured text. And we're going to talk about how you can do data extraction using neurosymbolic methods. And this part of the talk is based on our LLVM paper, if you would like to learn more. And this was led by my former student, Jocelyn Chen. Okay. So again, let me give you a motivating scenario for what we're trying to do here. So let's say you are on the job market and you have a bunch of job listings, for example, in the form of a big spreadsheet or a text file, and you want to filter all those job listings that are relevant to your particular search. For example, let's say you are interested in software engineering jobs in the US, so that's you only want to retain those listings. So just to give you an idea of what we're trying to do, if you have a spreadsheet that's full of entries like this one, clearly the first and the last one should be retained because .NET developer is a type of software engineer. Winter Park, Florida is in the United States. But the middle two should be filtered out because, for example, this is in Germany as opposed to the US, and paralegal is not a software engineer, and so on. So the question is, how do you do this data extraction task? Well, generally, when you want to do data extraction, one of the powerful tools that we have is regular expressions. So your first thought here might be, can I write a regular expression to do this? Unfortunately, if you think about it for a second, you'll realize that this is not a great fit for regexes. For example, how would you write a regex to match all the software engineering jobs, right? So for example, .NET developer, blah, 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 neither syntactically contains the word software, nor does it contain the word engineer. And similarly, how would you write a regex to match all of the US cities? Well, if you're very patient, you could maybe spend the whole afternoon hard coding the cities, but I think we can agree that this is not the best use of anyone's time. So this brings me to our approach, which is neurosymbolic. So in this work, we proposed a new neurosymbolic program abstraction that we call semantic regexes. And the idea behind semantic regexes is to extend regular expressions with LLM-based semantic reasoning. Okay, so in more detail, we're going to retain our traditional regexes, which we all love, in order to do syntactic pattern matching. But in addition, we're also going to augment it with large language models in order to do further semantic filtering over the match text. So in more detail, the idea here is rather than viewing a string as a sequence of raw characters, we're instead going to think of a string as a sequence of tokens where each token has some intrinsic meaning and various attributes associated with it. So for example, if I give you this string, from the perspective of a traditional regex, well, you would say this is the concatenation of a bunch of digits, a 2 followed by a bunch of zeros. But from a more semantic perspective, well, this is a string that represents a number, and that number has various properties, like it represents a positive number. It has the value 20,000 and so on. As another example, if I give you this string, AUSTIN, from the perspective of a traditional regex, you would say, well, it starts with a capital A followed by a bunch of lowercase letters. But if I asked any of you in the audience, you would say, well, that's a string that represents a city, and again, this city has various properties like being located in Texas, United States, and so on. And as a last example, if I give you these two strings, from the perspective of a traditional regex, the only commonality between these words is that there are two words that start with a capital letter and that are separated by a space. But if I asked any of you in the audience, you would say, these are celebrity person names, right? So we basically capture this using this notation that looks exactly like a refinement type. And in the context of semantic regexes, each atom has a base type associated with it, like a number or a city. And you can also have an optional logical qualifier. So it's a logical formula that allows you to further filter the match text. So for example, here, if you look at the second regex, it's telling us that whatever string that we match should correspond to a city. But we don't want just any city. We want a city whose corresponding state is, for example, Texas. Okay. So that's the syntax. Let's talk about the semantics. How do you evaluate them? In other words, if I give you a semantic regex and a string, how do you decide whether there's a match or not? So the evaluation of semantic regexes is going to be neurosymbolic. And specifically for the base type, we're going to consult an LLM and ask the LLM, does this string represent whatever, does this represent X, where X is the type like a city or person and so on. Okay? And if the LLM says no, then we say there is no match. Otherwise, we're going to proceed to evaluate the logical qualifier. And in order to do that, we're first going to do some sort of retrieval. So we're going to consult an external knowledge base, or this could also be a large language model. But we're going to extract the required attributes of that type. And this will allow us to parse this string as an object of the suitable type. And once we have that, we can symbolically evaluate our predicate. And based on that, if it evaluates to true, we say there is a match, and otherwise, no match. So going back to our earlier example, recall that we wanted to write a regex that can match all software engineer job listings in the United States. Now that we have these semantic regexes, we can achieve this task by writing a regex that looks like this. So basically, it's saying that the first part of the string should be some type of software engineer. And then there can be various stuff that we don't care about in the middle. But the end part of the string should represent a geopolitical entity. So GPE here sounds for geopolitical entity. But again, we don't want just any geopolitical entity. We want the country associated with this geopolitical entity to be United States. And so let's take a look at this string. How do we match it against this regex? Well, first, by consulting an LLM, it can tell us that .NET developer is indeed a type of software engineer. Winter Park, Florida is a geopolitical entity. And of course, the middle part will match .star. And then we're going to do retrieval. And we're going to consult an external information source to look up attributes of Winter Park, Florida. So for example, we're going to look up its country. And then we can symbolically evaluate our predicate. And based on that, we decide that there is, in fact, a match here. Okay. So we talked about the representation. Now let's talk about the learning algorithm. So as you all know, if you have some complex data extraction tasks, writing regexes can get quite annoying. And most people don't enjoy writing regexes. So instead of asking people to manually write these semantic regexes, we want to completely automate this data extraction task, again, using a programming by example approach. And as before, the idea is that the user provides a small number of examples. In this case, we need a few positive examples of strings that should be matched, and a few examples of negative strings that should be rejected. And we want to automatically generalize from those and synthesize a semantic regex that we can then use for data extraction on a much larger data set. So again, I don't want to talk about our learning algorithm in a lot of detail. If you're interested, I'll refer you to our Uppsala paper. But what I did want to kind of, again, highlight is this interplay between search and neural guidance and symbolic reasoning in the search algorithm. So as before, as in the first part of the talk, at the core, we have some sort of backtracking search. Again, this idea of top-down enumerative search. But here, rather than doing blind search, our top-down enumerative search will be guided by a large language model. And specifically in this context, given the positive examples, we use an LLM to predict the skeleton of the regex. So think of it as some sort of sketch. And then once we have that sketch, this is where we do type-directed search. So we have a type system that has a notion of subtyping. And we can use this type system to both guide the search and do systematic pruning of the search space. And furthermore, if synthesis fails, we can also use a combination of the type system and a basic form of program analysis to do fault localization. So we can identify what part of the sketch was problematic, and we can use it to do localized repair, and we can reprompt the LLM in a much more intelligent way. So the symbolic reasoning guides LLM prompting in this case. So again, quick highlight of our evaluation. So we evaluated this method on a bunch of data extraction tasks that were provided to us by a company called Sigma Computing that we were collaborating with at the time. And they actually had very interesting data extraction tasks that had both a syntactic pattern matching component to them as well as some semantic reasoning requirement. And they had a bunch of different domains involving email addresses, merchandise, log files, and so on and so forth. Okay? So to evaluate our method, we considered 3 baselines. So the first baseline is what I will refer to as regex. So here, rather than synthesizing a semantic regex, we're again learning a regex, but we're instead using a traditional regex. So this baseline allows us to assess the importance of semantic regexes as opposed to traditional regexes. Our second baseline is a purely neural approach, namely just GPT. So what we did here is we took whatever version of GPT was available at the time. I believe it was 3.5. But we provide GPT with all the positive and the negative examples provided by the user. And then given a new string in the test set, we ask the LLM, should this be accepted or rejected? Should it be matched or not matched? And our final baseline is a tool called Flash GPT. So I'm sure many of you are familiar with FlashFill and that family of tools. So this comes from the FlashFill family of tools from the Microsoft Prose team. And this is also specialized for a tool that's specialized for data extraction. And it's also neurosymbolic, but it combines LLMs and regexes in a very different way than we do here. So to compare these approaches, we provide all of them the exact same input. So every tool gets 3 positive examples and 3 negative examples. And we measured relevant statistics on the test data. So what are relevant statistics? One is, of course, recall of the strings that we should extract. What % did we actually end up extracting? Another important statistics is, of course, precision of those strings that we extracted. What % are actually relevant? And of course, if you want to look at the combination of precision and recall, the typical metric is F1 score. And as you can see from this small table, so in terms of recall, FlashGPT and our method are pretty similar, 0.83 and 0.84. They both do better than the other 2 baselines. But in terms of precision, our method significantly outperforms the other baselines, which of course yields in an overall the best F1 score. Okay, so to recap, in this part of the talk, we looked at an application of neurosymbolic programming to textual data, and we saw how it enables flexible pattern matching by combining the power of traditional regexes with large language models to do more semantic reasoning about textual data. Okay, so in the last application domain that I'm going to talk about, we'll consider a more futuristic application domain, namely robotics. And again, if you would like to learn more, this part of the talk is based on our PLDI'25 paper that was led by my student Noah Patton, who is co-advised with a robotics faculty at UT. Okay, so I always like to give a motivating scenario. So for this part, suppose that you bought a new robot. I told you it was going to be more futuristic, but let's say you have a new robot. This robot has been trained to do certain tasks, but not others. And now you want to teach the robot some new task that you in particular care about. So for example, as you can see from this image, I love, I'm a big coffee drinker, so I always have dirty coffee mugs sitting around in my house. So I would personally like to teach my robot to collect dirty coffee mugs lying around in my office or my house, right? So there's a common approach to doing this in the robotics community. This is a common approach for human-robot interaction is this idea called learning from demonstration, or LFD. And the idea here is that the user provides a physical demonstration to the robot, and the goal of the robot is to generalize from the demonstration and learn a policy that can be used to perform similar tasks in slightly different environments. Okay, so of course, there's a lot of work on LFD in the robotics community. We're clearly not the first people to talk about it. So for example, you might have heard of approaches like behavior cloning, which is a type of imitation learning, or there's this idea of inverse reinforcement learning. So there's a lot of work out there. But if you reflect on all of those, I would say that one common theme across all the existing work is that they represent the policy using a purely neural representation. And I don't mean to undermine any of this existing LFD work. There's many settings where these ideas work really, really well. But there are also some areas where existing techniques don't work very well. And a typical example of such domains is what robotics is called long horizon tasks. So in a nutshell, long horizon tasks are these kinds of tasks that require the robot to perform a sequence of interrelated actions over a longer time horizon, right? So existing techniques don't do very well with long horizon tasks. And additionally, they also have the usual problems like lacking interpretability and requiring significant amount of data, which in this context means that the user needs to give lots of demonstrations, which can be tedious. Okay. So to address these shortcomings in the context of long horizon tasks, we developed a new neurosymbolic approach called PROLEX. And here, rather than having a purely neural policy representation, we instead represent policies in a neurosymbolic DSL. And as you saw in the other parts of the talk, here we're going to be using neural components for perception as well as motion planning. And we're also going to use symbolic constructs like conditionals, loops, and so on to capture repetitive aspects of the tasks and for doing better decision making. So going back to a similar example to what I was saying earlier, so let's consider the task of collecting dirty sheets from around the house. So you can express a policy for doing this in our domain-specific language. So as you can see, for this application domain, we have this imperative language with a bunch of nested for loops, assignments, and so on. And if you stare at this for a second, you will see that there's this atomic command called scan for a certain type of object. So this is allowing the robot to locate objects of a specific type. And this is, of course, used for perception, and it's implemented using a vision language model. And as you can see here, we also have atomic commands like open, grab, close, and so on. These also correspond to pre-trained neural networks for basic skills that pretty much every robot needs to be able to do. And of course, these are all composed together using our symbolic constructs like sequencing, loops, conditionals, and so on. So again, that was the representation. Now let's talk about the learning task. So remember that here we're trying to do learning from demonstration. So the input to the learning algorithm will be a demonstration. And the demonstration, we represent it as a pair. One part of the demonstration is a trace. So it's basically a sequence of atomic actions that have some externally visible effect. For example, open, put in, and so on. And recall that the demonstration is also, of course, performed in some environment. So therefore, the other part of the demonstration is some representation of the environment in which that demonstration is performed. So given these two inputs, the goal of the learning algorithm is to learn this robot execution policy. So again, I don't want to talk in a lot of detail about the learning algorithm, but once again, I did want to highlight the synergy between LLM-guided search and program analysis here. So as before, our top-level algorithm is based on this top-down enumerative search, but here we use LLM guidance in order to provide common sense priors during the search process. So what do I mean by that? Well, let's say in our partial program, we have a statement that says place some object in a laundry bin. And let's say it has some unknown conditional that we're trying to synthesize. Well, if you consult an LLM, it can tell you that you're probably much more likely to check a property like, is this object clean or dirty, as opposed to some other property like, is it wrinkled, does it have a certain texture or color? So here, by using LLM guidance, we can get common sense priors about the real world in which the robot operates. Now, it turns out that even more importantly than LLM guidance, a huge requirement for making this work that we found is to use program analysis. So what we do here is, given a partial program, we use a form of abstract interpretation to over-approximate all of the traces that could be generated by that program. And if we find that the user's demonstration is not among those over-approximated traces, then we definitely know we're at a dead end, and we can, again, use it to do systematic pruning of the search space. So program analysis for the win once again. So again, some highlights from our evaluation. So we implemented this in a tool called Prolex, and since our target is long horizon tasks, we evaluated it on an existing data set called behavior. So this is a data set put out by the Stanford Robotics folks, and we chose this data set because in a prior paper, they showed that existing imitation learning or reinforcement learning techniques don't work for these kinds of long horizon service tasks that are performed in household environments. So they basically, existing neural techniques perform pretty abysmally in this setting. They basically cannot do any of the tasks. And using our method, it's far from perfect, as you can see, but what we did find is that given a 2-minute time limit, our tool was able to synthesize a program consistent with the demonstration for 80% of the benchmark. So you can think of it for 80% of the benchmark, synthesis succeeds. But of course, if synthesis succeeds, it may or may not produce the ground truth. And we find that among the programs where synthesis terminates, 81% of the learned programs actually correspond to the ground truth and generalize to other environments. So overall, the success rate here is around 65%, so there's significant room for improvement, but still, we see a big improvement over purely neural techniques. Okay, so in this last part of the talk, I'm going to reflect on a cross-cutting concern across all of these different application domains that we looked at, and I want to talk about how we can ensure trust in neurosymbolic learning. So first, what the heck do I mean by trust? Well, what I mean is that in all cases, the synthesizer, if it doesn't time out, it returns you a program. But how can you, as the user, have any confidence that it's actually returning or synthesizing the program that you want? One solution to this problem is you can go ahead and ask the user, please go ahead and inspect the program, give me a thumbs up or a thumbs down. And I would argue that this is probably easier than inspecting the weights of a neural network, but I think we can all agree that this is suboptimal, right? It's not feasible for most end users who may not have programming expertise or who may not be familiar with the DSLs that we're using. So a better solution to this problem is this idea of active learning. And the idea behind active learning is rather than asking the user to passively label some data, you interactively query them. You reason about what's the most informative input, for example, for the user to label. And you interactively query the user until you're very confident that you've converged to the right program. So for example, going back to our image editing setting, rather than asking the user to passively label a bunch of images, the synthesizer can internally reason what's the most informative image in this data set, and they can ask the user to label that particular image as opposed to some random image, right? And the user provides an answer, and based on the user's answer, we're going to refine our hypothesis space. And we want to keep doing this until some termination criterion is reached, for example, until all programs are observationally equivalent on the inputs that we care about. And very importantly, when you do this active learning, the goal here is you would like to do this in a way that minimizes the number of rounds of user interaction, because if you ask lots of questions to the user, that's not particularly helpful. Now, again, we're not the first people to talk about active learning in the context of program synthesis. There's actually lots of great work from the PLDI, UPSLA, POPL community on active learning for program synthesis. I highlighted some of the prior work here. But one kind of common theme among all the prior work is that they target the traditional purely symbolic program synthesis setting. And what that means is that if you apply them to neurosymbolic programs, they're not going to account for possible mispredictions of neural constructs. And as a result, they may end up erroneously eliminating the desired program, meaning that synthesis will fail. So this is probably not obvious, so let me illustrate how that can happen through a concrete example. So a very simple example. So suppose that I want to synthesize a program for cropping all of the cats in a given photo, right? And you can achieve this task using this very, very, very simple program in our DSL that looks like a one-liner that looks like this. If it's a cat, then apply a crop action. And now if you query the user and ask the user to label this data, of course, they're going to tell you that this is the desired output. Right? So far, so good. But here's the problem. Recall that this construct, this predicate is cat, is actually implemented using a neural network. In fact, it's implemented using 2 neural networks. To evaluate this, you first need to do image segmentation. And once you do that, you also need to do image classification. So if either of those has a problem, it's entirely possible that you may misclassify some of the objects in the image, right? So for example, for this cute picture here, let's say that the object classifier gets confused by the snow on the dog's nose. So let's say it ends up misclassifying the dog as a cat. So instead of thinking there's a cat and a dog in this image, we now think there are actually 2 cats. Okay? So what's the problem? So recall that during active learning, we're going to evaluate each program, and we're going to check if it, if I execute this on the input labeled by the user, I want to check if it actually matches the user's output. But now, if I execute this program on this image, I'm going to end up with 2 cropped images because we think this dog is also a cat. And obviously, this is not going to match the user's answer. And as a result, we think that this program is wrong, even though this is actually the desired program that would have worked on most of the images in the user's data set, but we're going to end up eliminating it, and which means that learning will completely fail. So in our recent work, the question that we asked is, how do we ensure that we return the correct program to the user, even when these neural components can have mispredictions? And the key idea that we're exploring is to leverage a new type of semantics called conformal semantics of neurosymbolic programs. And the idea here is to build on top of this rich literature on conformal prediction in the machine learning community. And if you're not familiar with conformal prediction, in a nutshell, the idea is that you want to return a set of predictions rather than a single prediction. And in doing this, you want to train the neural network in such a way that the ground truth is going to be contained within this prediction set with very high probability. So you can think of it as you have a different optimization objective that emphasizes correctness rather than precision. So in our ongoing work, we are exploring this technique that allows you to efficiently propagate conformal prediction sets through neurosymbolic programs, and does this in a way that takes the user's answers into account. And building on that conformal evaluation method, we are working on an active learning algorithm that leverages conformal evaluation to select the most informative queries to ask to the user. And ultimately, the guarantee that we get is upon convergence, we want to make sure that the program that's returned to the user is likely to be the desired program with very high probability. So unlike a lot of formal methods techniques here, we don't get hard guarantees. We can't say with 100% confidence you're going to get the desired program, but still you get this probabilistic guarantee, which I would argue is better than having no guarantee at all. And furthermore, this probability is a value, it's a knob that can be controlled by the user. Okay, so kind of to wrap up, I'm personally very excited about neurosymbolic programming. I think it really opens up new avenues compared to just purely neural or purely programmatic approaches. And by, as I kept emphasizing throughout the talk, by using neural networks, we get the ability to deal with messy real-world inputs like images and unstructured text. But at the same time, by using programming languages, we get modularity, we get interpretability, and we get more data-efficient learning. And I'll conclude by talking about a few directions for future work, if any of you in the audience are also interested in joining this neurosymbolic program synthesis area. So one interesting direction is, as I kept emphasizing, in a lot of the work that we've done in my group, the neural components in the DSL correspond to pre-trained neural networks. But one interesting idea is that can you actually co-learn the symbolic representation and the neural representation, for example, by doing fine-tuning on the neural networks, especially if you can't find a good matching program. Another interesting thought here is, again, as I kept emphasizing, there is a lot of expertise on, there's a lot of emphasis on DSL design, and this requires a lot of human expertise. And the idea here is that instead of relying on humans for DSL design, can we semi-automate this process, for example, by coming up with new program abstractions, or maybe slightly modifying the existing semantics of constructs in order to adapt to slightly different domains. And last but not least, I think there's also this very important question is how do we account for uncertainty when you execute neurosymbolic programs? And I think this is especially important in safety-critical settings like robotics. So for example, by explicitly reasoning about uncertainty, you may be able to detect when the robot is about to do something unsafe, and then you may fall back on a more conservative course of action, or for example, ask the user for help. And last but not least, I do want to thank all of my collaborators. Unfortunately, I didn't get a chance to fit all of them on the slide, but I did especially want to acknowledge my students who led these projects, Celeste, Jocelyn, and Noah, as well as 3 key collaborators, Osbert Bastani from Penn, who works at the intersection of ML and PL, my colleague Greg Durrett at UT Austin, who works on natural language processing, and my colleague Joydeep Biswas, also at UT, who works on robotics. So that's my talk. If you have any questions, I'm happy to take them.
Okay, folks, please come on up to the microphones and make sure to introduce yourself.
I can hear you, Manu. If you want, I can repeat the question for you. Okay.
Hi, everyone. Manu Sridhar in UC Riverside. Really cool talk. One thing that was going through my head is all this buzz around like agentic AI, and it seems to be almost the inversion of what you're doing, right? Because there it's like you let the large language model run the tools, and in a lot of your synthesis techniques, you're kind of running the large language model as a subroutine. So I was wondering if you would kind of agree with that characterization and kind of
That's a great observation. Yeah, I hadn't actually thought about it in that way, but when you say it like that, yeah, it seems like the inversion of agentic methods.
Yeah, and as a PL person, I like your methods a lot more. But I was curious if you've like thought about whether the agentic stuff kind of fits into this agenda also.
I guess one way to look at agentic methods is that you're composing different LLMs that are good at different things. So in some sense, I think you can view them in a more uniform framework. But it's a really interesting observation. Yeah.
Cool. Thank you very much.
Sure.
Hi, Xiaokan Chiu from Purdue University. Thank you for the excellent talk. So I think we all agree that neural approaches and symbolic approaches are complementary. But I think both fields are rapidly evolving, and what we consider weakness or strength can be no longer the case next day or next month, right? So we may consider that language models are good at recognizing cities, but not good at counting. But maybe next month we have a stronger model, or for symbolic approaches, we may consider some tasks are too big to search with today's algorithms, but next day we have a better algorithm. So I just want to hear your thoughts or experience on building neurosymbolic learning algorithms on top of this ever-changing
I
online
think
techniques.
you have a good point, and like I do think we need to be very cognizant of the fact that LLMs are constantly improving. But I think I did highlight some of the things that I tried to highlight are universal, and there are problems that are going to remain no matter what neural method that you look at. At the end of the day, these things get like bigger and bigger, so it's like your interpretability is definitely going to remain a problem, verifiability is going to remain a problem, and so on.
Yeah, thanks.
Sure.
Check. Okay. Hi, this is Luigi from Peking University, and I'm pretty curious about the definition of equivalence in your slides, because you mentioned observational equivalence, and also in active learning we need to check the equivalence of users' response and the program. Yeah, but I guess a pretty significant difference here is that, for example, for the case of image processing, the user's response may have some noise, and also the output of the neural network will have some noise, right? Because if we want to crop up image, then there are many different, slightly different ways. So I'm curious about whether we need some, for example, new definition of equivalence or new semantic approach to tolerate such kind of noise.
So you brought up two different sources of kind of ambiguity here. One of them is like the one that arises from the neural network mispredictions, which is what our, like the last part of the talk aims to address. But for the other thing that you talked about, namely that there are many ways you can crop the image, I absolutely agree with that. But in this image search and editing work, in order to deal with that kind of noise, what we basically allow the users to edit the image through some kind of like graphical user interface where it basically like shows bounding boxes, and then the user can only apply a crop action to that bounding box area.
Oh, that makes sense. Yeah, thank you.
Sure.
Hi, I'm Bongjin from KAIST, and I was thinking what would be the ultimate application when this neurosymbolic AI is really realized. And I think the application would be the automotive, like self-driving cars. And the really difficult problem to applying this neurosymbolic AI technique to automotive is that it's not really easy to encode our knowledge of driving into this DSL. And the second problem is the driving knowledge always is evolving. Like, for example, in Korea, there was kind of really messy situation like, can I turn right on the green light? And the law changes like 3 times or 4 times during the past 2 weeks. So yeah, it was really crazy. And it's really easy to update the LLM part in the neurosymbolic system, but but if, let's say we somehow encoded our knowledge into DSL, but it's not really hard. It's hard to update some part in the DSL automatically when we have a new knowledge. So I want to hear your thoughts about this problem.
So can you state it as a question? You said you made a lot of points there, so
Yeah.
I was like not quite sure what's the part that you want me to address. I mean, for example, I think we can have a lot of discussions about what's the ultimate, success, like it's like asking when do we think we did AGI, right? So I don't know what's like the equivalent for neurosymbolic program synthesis, but it will be helpful if you can kind of distill your question.
The first thing I think there's a tension between what part should be an LLM part or what part should be the symbolic part. So at least I want to hear your experience of designing those systems.
That's a great question. There is indeed such a tension. So basically, what we do is we ask the question when you're designing a DSL, for example, in the image context, what are they good at doing and what are they not good at doing? And you basically the existing methods are good at image segmentation and object classification, so you use them and then you basically based on their outputs, you try to glue everything together using symbolic constructs. So I think that's an evolving thing rather than a static thing. So yeah, it has to do with the earlier point I think that Rui was making, which is that LLMs are constantly improving, and that means that probably the design of these DSLs also needs to improve.
Okay, the second point was,
I think let's do one last quick question, actually. No.
No.
All right, really nice talk. So I'm actually thinking about the LM and the train of the MCP. So there are more and more effort of connecting LM with various different application interfaces. And I want to see your thought of how this train will affect your approaches, because I see the kind of the bottleneck to the scalability is the DSL and requiring to design DSL if there are more new agent gets new interface application gets connected to LM agent, and hoping to automate tasks, it would be requiring to design like update the DSL or something. So
I think you're asking a pretty open-ended question, so maybe it will be more productive if like we you know take this offline and have a longer conversation.
Okay, let's all thank Ishil again for a fantastic talk. If you are a speaker or session chair for the next session, please make sure to get set up, test your AV, etc., and we will see you all soon.
Is my okay? Cool. All right, let's get started for this Compiler 2 session. So my name is Michael Stoiber. I'm at TU Berlin, and I will be sharing the session. We will have 5 very interesting talks, and we will start with the first talk from Shan, please.
Okay. Hello, everyone. I'm Shan Huang from East China Normal University. Today, Hello? Hello? Okay. I'm Shan Huang from East China Normal University. Today, I'll talk about robust-defined debug location updates in LLVM while control flow conformance analysis. When compiling user programs with flag-G, compilers would generate a critical compilation metadata named debug information along with the binaries. The generated debug information enables a variety of important program analysis techniques like debuggers, profilers, sanitizers, tracers, and coverage collection. Due to its usefulness, modern software projects usually recommend adding the -G flag to improve the quality assurance support. Debug location information, one important kind of debug information, maps low-level instructions to the statements in source code. For example, assuming we have the following C code and compile it with the flag -G, when debugging, the debugger could show where the program reaches, reading the debug location information embedded in the binary, and show the corresponding source code while a simple mapping process. Another example is that when running programs instrumented by address sanitizer to find memory bugs, address sanitizer uses debug location information to report where the program crashes. In LLVM, debug location is a kind of metadata attached to LLVM IR instructions. Here is an example. In the same C code, the subtraction expression A-1 in line 3 is compiled to this sub-instruction in LLVM IR. If we enable debugging compilation, this instruction would be attached with an additional compilation metadata, which is the debug location. It's easy to see that the first 2 fields of the debug location map the instruction back to line 3 and column 17 in the source code. To use such information to perform reliable program analysis, we wish the mapping to be accurate. However, compiler optimizations may invalidate debug locations. Consider the function recursion in the C code. I'll show you how compiler optimization invalidates debug locations on the control flow graph of its LLVM IR. The multiplication expression in line 7 is compiled to the LLVM IR instruction mall in the basic block if.else. In this and the following examples, we use the line number in the source code to denote the debug location attached to the instructions. Assuming we optimize this multiplication by replacing it with an addition, a new instruction add is created to replace the original instruction mall in the AR. And the new instruction add it has no debugging location attached, which is denoted as line 0. Unfortunately, after this instruction replacement, there is a debug location loss in this program because the debug location of line 7 is discarded along with the deleted instruction mall. As a result, debugging or profiling the line 7 become infeasible. To avoid this debug location loss, the debug location attached to the deleted instruction could be preserved to the semantically related new instruction, which means we copy the debug location of the instruction mall to the instruction add. This process is called the debug location update in LLVM, which is required to be written by optimization developers in optimization code. Specifically, the debug location update consists of 3 parts: the source instruction from the unoptimized program, to which the attached debug location is used for the update, the destination S' from the optimized program, to which the attached debug location is updated, and the update operation, which uses the debug location attached to the source instruction to update that of the destination instruction. Currently, there are 3 update operations in LLVM, which are preserve, merge, and drop. To make debug information in optimized programs reliable, the debugging location updates should be correct. However, manually updating debug locations is error-prone, leading to update errors that subsequently cause debug information bugs. Next, I'll give you an example. In the same C code, we can see that line 5 is in a dead branch because the value of the variable a always equals 2 when encountering the second if condition. And line 7 is thus the live branch. However, if we compile this C program with LLVM optimization, tail call elimination, when debugging the optimized code, the debugger shows that the execution enters the dead branch, although the real program state is correct. And this is a debugger information bug caused by a debugger location update error in optimization tail call elimination. I'll demonstrate the root cause of this bug also on the control flow graph of the function recursion. After the front end, the addition expression in line 5 is compiled to the instruction add with a debug location pointing to line 5 in the if.then2 block, which is the dead block. After the optimization, the control flow graph changes, but the branches remain unchanged. The tail call elimination clones a new instruction add prime from the instruction add and inserts the new add prime to the live block if.else. Meanwhile, the debug location of add is preserved to end prime. However, this is a debug location update error. Because when the program executes along the path gamma and encounters end prime, the debugger reads the debug location pointing to line 5 and shows that the program execution enters the dead branch, giving the misleading information to users. Such misleading information severely impacts the reliability of the techniques and using debug locations. Recently, several works leverage testing to find debug information bugs. They use debuggers to debug both the unoptimized program and the optimized program, comparing the debugging traces. Any inconsistency indicates a debug information bug. For example, when debugging the unoptimized code, the debugger never shows the deadline 5. However, when debugging the code optimized by tail call elimination, the debugger shows that the program execution reaches the deadline 5. Thus, this inconsistent debugging behavior indicates a debug information bug, although they are effective in finding bugs. Lacking the knowledge of the optimization passes, they cannot help locate and fix update errors. In this work, instead of detecting debug information bugs, we propose a robustification technique which finds and fixes debug location update errors. In addition to the unoptimized and optimized programs, our robustification technique also analyzes the LLVM optimization passes, determine the correct updates, which is then used to find the update errors and generate patch skeletons. Central to our robustification approach is determining the correct debug location updates in LLVM optimization passes. So for robustifying debug location updates in LLVM, there are two unique challenges. First, how to identify source and destination instructions. Second, how to determine the correct update operations. To tackle the first challenge, we need to understand the destination and the source instructions. In the previous example, we showed an update using the update operation preserve. In this example, we can see that the source instruction as from the unoptimized program is that the source is the instruction providing the debug location for updating. The destination instruction S prime from the optimized program is the instruction semantically related to the source instruction. For example, the destination instruction is a replacement of the source instruction in this case. Meanwhile, the destination instruction is the instruction whose debug location should be updated. In this example, the destination instruction is a newly created instruction with an empty debug location. So when it is inserted into the IR program, it can be assigned a new debugging location. According to this understanding from the LLVM class instruction, we extract 4 categories of instruction manipulation APIs, which can capture in the source and destination instructions. To use them, we monitor the execution of the optimization passes and record the instruction operands and the corresponding variable names of these 4 kinds of APIs. After identifying the source and destination instructions, the second challenge is to determine the appropriate update operations for them. To tackle this challenge, our observation is that the debug location is an update in an optimized program, and its optimized counterpart should satisfy a conformance relation, which requires no extra debug location appears on control flow paths in the optimized program. In the previously discussed debug information bug, debug location of line 5 does not occur on the path gamma before the optimization. However, after the optimization, the debug location of line 5 appears on this path. And thus, it's the extra debug location for this path gamma, violating the conformance relation. To enforce the conformance relation, we should avoid introduce such extra debug locations into paths in optimized programs. From this example, we can see that the root cause of extra debug locations is that the destination instruction add prime appears on a control flow path that does not contain the source instruction add. Therefore, we propose control flow conformance analysis to determine the appropriate update operations that enforce the conformance relation. Specifically, the control flow conformance analysis checks whether there is a control flow path which contains the destination instruction but does not contain the source instruction. If there exists such a path, the update operation is dropped. If there is not, the update operation is preserve or merge, which means we keep the debug location. Recall the previous code optimization example in which the update operation preserve is used. In this example, the destination instruction and the source instruction are in the same block, indicating that all control flow paths passing through the destination instruction must pass through the source instruction. So the check of control flow conformance analysis fails. The update operation should be preserved. In the example demonstrating a debug information bug, the destination and the source instruction are located in different branches of the same if condition. So there exists a path which contains the destination instruction but does not contain the source instruction. As a result, the update operation should be dropped to avoid introducing an extra debug location to that path. However, as we discussed in this bug, the optimization tail call elimination preserves the debug location from the source instruction to the destination instruction. Therefore, using the determined update operation drop, we can find this debug location update error. Meanwhile, the determined update operation can tell us how to fix this debug location update error. That's how we robustify the debug location updates in LLVM. We have implemented the robustification technique in a tool named Mentalog. The first part of Mentalog is a standalone path instrumentation tool, which instruments the instruction APIs and the entries and the exits of LLVM optimization passes. The second part is a lightweight built-in library for LLVM, which implements the instrumentation hooks, the control flow conformance analysis, and the patch scatter generation. To evaluate Mentalog, we run it on all 80 scalar optimization paths with the corresponding regression tests and the path inputs. As a result, with the help of Mentalog, we have successfully fixed 46 update errors in 18 optimization passes using 21 pull requests. In addition, we have fixed one incorrect and one incomplete update example in LLVM documentation according to our control flow conformance analysis. You can check out our paper for more evaluation details. To sum up, we improved debug information quality from a new perspective. Instead of testing, we robustified debug location updates while analyzing both compiler optimizations and LLVM IR programs. To achieve that goal, we designed the first robustification approach, of which the core is control flow conformance analysis for determining the correct update operations. Finally, we implemented tool Mintalog, helping find and fix 46 debug location update errors in LLVM. Thank you for listening. That's all.
Okay, we have time for a couple of questions. So then let me ask you a question.
Okay.
So this is specific for maintaining or improving the debug information because they get lost when you do optimizations.
Yes.
Does this also apply, or do you think this could generalize to other forms of metadata you might want to kind of maintain while you perform optimizations?
Okay. I think this is specific to the debug location updates in LLVM, but this approach maybe can be generalized to other compilers like GCC, which maybe they use the same mechanism to maintain the debug locations. But for other compilation metadata like debug values or other something, we need to find another way to address them. Okay.
Hey, great talk.
Okay.
Konstantinos Kallas from UCLA. So as far as I understand, the technique that you use is able to fix bugs essentially in this information preservation. Could you also see this being extended to fully automate this debug preservation, essentially lowering even more the developer overhead? Yeah.
Okay, that's a good question. Actually, we I'll see. Actually, we can determine the correct update operations, but to write the code, we can do a simple skeleton translation. So we just output the skeletons, but the actual code should be written by human. So, so in this project, we write them by ourselves and send them to the LLVM community. Yeah.
Cool. All right. Then let's thank Shen. The next speaker can come up. All right. And the next talk will be given by Ling. And he will be talking about verified compositional compilation.
Okay. Oh, cool. Thanks for the introduction. I'm Ling Zhang from Shanghai Jiao Tong University. So today I'm going to present our recent work on verified compilation. Particularly, it's about verified compilation of multi-threaded programs which may share stack data between different threads. This is a joint work with these people. First, I will introduce the background of verified computational compilation, or VCC for short. The compiler correctness is usually defined as refinement between semantics. Here, this notation denotes that the semantics of M1 is refined by that of M2. So for, So for example, the state-of-the-art verified compiler for C ComSearch, it compiles the source program foo.c into the target program foo.s. Here, this refinement ensures that all the possible behaviors of the target program is included by that of the source program. So any desired property on the source program can be preserved to the target program. For open programs, the modules are separately compiled into target programs. And as VCC, we need to ensure that these refinements can be composed to get the refinement of complete programs. So we need to formalize and verify the interaction between these open modules. For sequential programs, these interactions are mainly in the form of function calls and returns. For multi-threaded programs, similarly, we prove the compilation in the form of refinement. But the point here is different threads may interfere with each other via context switches, which is much more harder to be verified than function calls and returns. So there has been a great amount of work on achieving different kinds of VCC. Here we only focus on the extensions of ComCert, which is usually used as the foundation of verified compilation. So computational ComCert first achieves the verified compilation of open programs. Then thread-safe ComCert-X and CAS-ComCert achieves verified compilation of multi-threaded programs. However, the shared stack is not supported in these works, which means one thread cannot access the stack data allocated by another thread. This has been an open program since then. And recently, we have more works on the VCC for sequential programs, which introduce new techniques for the reasoning of memory. So this work is going to use the framework comes from nominal ComCert and ComCert-O to address this open problem. So that's why it's named ComCert-OC, C for concurrent. So now let's see why shared stack is a problem in multi-threaded programs. Here we have a running example of parent and child threads. The parent thread will allocate this to local variables I and TID. It then uses pthread create to create a child thread and pass the address of I to it. Then the child thread may update the value of the shared variable I, and the parent thread will join it and print the value of I. I think this is a very common practice in multi-threaded programming, where the two threads share a shared variable I, but it's not formally supported by any existing computational compiler. Here the main challenge is how to verify the simultaneous stack sharing and protection, where the variable I is shared between these two threads, while the another variable TID should be protected from the child thread. Otherwise, the pthread join may find the wrong target, right? So one sentence for our contribution is we, for the first time, achieved verified computational compilation for a multi-threaded program with shared stacks. Our work is based on reliability guarantee reasoning, which is a very common technique in computational verification. Based on it, we introduced two key ideas: the threaded open simulation for final-grained reliability guarantee conditions, and the threaded equivalent memory relation for memory protection. We have also successfully integrated our framework with ComCert-O, which gives us ComCert-OC includes 18 of 20 parsers in ComCert v3.13. Using this compiler, we are able to achieve verified compilation of heterogeneous programs. So in the remaining of this talk, I will be mainly focused on the two ideas and briefly introduce our applications. Notice that the following discussion is based on cooperative multithreading, where context switches are caused by thread primitives. The connection to preemptive multithreading is left for future work. So I will start with the first key idea. I will first talk about the background for sequential programs and the challenge in multithreading, and finally our solution. So the background refinement relation between sequential programs is usually defined as open simulation. As you can see, the program states of source and target programs are related at each point during the execution. And when they call external calls, they make a rely condition on the environment. And on the other hand, this simulation provides a guarantee condition from the initialization to the finalization. Note that rely guarantee conditions in such open simulation are only defined for complete function calls, which means we know absolutely nothing from the initialization to external calls or from the returns to the finalization. Symmetric rely guarantee conditions can enable the composition of open simulations. As you can see in the example on the right, if the rely condition of the caller can be satisfied by the guarantee provided by callee, then these two refinements can be composed. Let's see a concrete example of compilation, or here is the optimization at the source level. This is two sequential programs. this was sequential program caller, where J is caller's private variable. You can see it's only used in the printf and it's never leaked. So the compiler may remove it out of the memory and propagate its value to the printf command as a constant. We shall agree this simple optimization is correct, while this correctness actually relies on the assumption that the J in source variable is never changed by the external callee, right? So from now on, we will focus on the execution and the interaction between source programs. For simplicity, again, this rely condition should be satisfied by the guarantee condition provided by the callee. Therefore, they can be composed. Now let's see why this doesn't work for multi-threading. This is our running example for parent and child again. The parent thread will create and the switches to the child thread. And similarly, we have a rely condition that TID is not changed by the child. One possibility of the execution here is that the child thread ends its execution, it returns and switches back to the parent thread. In such situation, it's pretty the same as the sequential case. The guarantee condition of the child function can guarantee that it does not change the private variable TID. So it seems like context switches could be treated similarly as function calls. But we have another possibility, that if the child thread switches back before its return, in such situations, the open simulation of child provides no guarantee to enable the composition, because remember that rely guarantee conditions in open simulation is only defined for complete function calls. So the problem here is we need a guarantee condition for partial execution. Now let's extend the open simulation for sequential case to get our threaded open simulation for multi-threaded programs. The first step is to introduce context switches. We use the same rely on external calls and the context switches because they look similar from the perspective of the open module. The second step is to introduce internal guarantee of internal executions to satisfy the rely of context switches. The guarantee condition from initialization to finalization is preserved and renamed into external guarantee. So this is a complete diagram of threaded open simulation, which we use it as the refinement between open multi-threaded programs. The rely condition can be satisfied by different guarantees in different situations. So now we still have a remaining problem, is how to define these rely guarantee conditions for all programs and for all possible executions in the multi-threading. To answer this, the main challenge is actually the general definition of memory protection. So here comes our second key idea. It's called threaded crypt key memory relation. It's the same pattern from background to challenge and solution. Again, this is our example of the sequential programs. Here we present the picture of memory states. Again, the caller has a rely condition that the variable J should be unchanged during this unknown external call, and is satisfied by the guarantee condition provided by the callee. So the rely guarantee condition here for the memory protection is that the private variable J should be unchanged during this external call. This memory relation is usually can be described using memory accessibility. It's a general definition from crypt key relation. To establish such accessibility from M1 to M2, which basically says that M2 is a valid successor of M1 after an external call, we need to do two steps. The first step is to mark the private regions in M1. In our example, it's very simple. It's just the variable J. But the formal general definition of private regions is actually related to the compilation. And I do not have time to discuss it here. You can find it in our paper. The second step is to ensure that these regions are unchanged in M2. Quite simple. So also, the guarantee condition provided by the callee is defined using the same memory accessibility. So in summary, for sequential programs, the rely guarantee conditions are defined using the same accessibility, so they are symmetric and can enable the composition. Now let's see why this doesn't work for multi-threading. This is again the parent and child thread example. The difference is here, we assume that the child thread also allocates its own private variable k. And the execution starts after pthread create, which means child thread is created at the first in the very beginning, the same as its private variable k is in the initial memory. Then similarly, the parent switches to the child thread, and the child thread may modify k and use it to increase the child variable I. Then it switches back to the parent. In this example, the direct guarantee, you can see is only TID should be protected during this context switch, while K could be changed by the internal execution of child. This is distribution. So if we try to use memory accessibility to describe these conditions, we'll see it fails because it cannot distinguish between TID and the K. They are both private variables in source programs. The only difference is they are allocated by different threads. So the problem here is the coarse-grained protection of private memory for all threads is not sufficient. So what we need is a finer-grained memory protection for each thread. So here comes our solution. It's called threaded encrypted memory relation. The key point here is we define two different memory accessibilities. The first line is external accessibility, which requires that the private memory of the current thread is unchanged. Well, the internal accessibility requires that the opposite, the private memory of the other thread should be unchanged from M1 to M2. Using these accessibilities, we can define the memory evolution in the relay guarantee conditions like this. As you can see, the relay condition and the external guarantee are defined using the same external accessibility, while the internal guarantee for partial executions are defined by internal accessibility. Now let's revisit our example. Here, the relay condition of the parent from M1 to M2 is defined using external accessibility, which assumes that TID is unchanged as its local private variable, while K does not need to be protected because it is external variable allocated by the child thread. On the right, the internal guarantee of the child thread also ensures that TID is unchanged, but as its external variable. So, and its local variable K can be changed by its internal executions. So as a brief summary, these two different memory accessibilities make sure that rely on external calls can be satisfied by external guarantee of the callee, which is pretty the same as the sequential case, and rely on context switches can be satisfied by internal guarantee of all other threads. Now, based on the two new mechanisms for relay guarantee conditions and memory protection, we are able to support verified compositional compilation of multi-threaded programs with shared stacks. Now I will briefly introduce our applications to demonstrate the feasibility of our approach. The first application is the ComSoL-OC, which is a verified compositional compiler for C using POSIX primitives and with shared stacks. To integrate our framework with ComSoL, we need to first implement the key ideas and update the proofs of individual passes in the ComSoL. Then we need to compose the multiple compilation passes to get the compiler correctness from source to target. We also need to compose the separate modules and threads. This integration actually took us 10% months and 20.3K lines of code in total. So there are quite a lot of technical challenges in this integration, but I don't have time to discuss them here. If you're interested, please read our paper. Another application is the verified compilation of a heterogeneous multi-threaded program. This is actually the running example in our paper, which includes a client and server both written in C. The client will create a child thread for the server, and the server will further call an external call, which is actually implemented in the handwritten assembly encrypt.s to do some encryption. To verify this example, we shall first introduce the specification of encrypt.s and verify it using threaded open simulation, which is exactly the same notion of the compiler correctness. Therefore, these three refinements can be composed to get the backward simulation between closed multi-threaded programs. So for conclusion, to the best of knowledge, we are the first time to achieve verified computational compilation of multi-threaded programs with shared stacks. I have introduced our two key ideas: threaded open simulation for like guarantee conditions and threaded equilibrium memorialization for the memory protection. We have also developed computational and used it to achieve verified compilation of complete programs. For future works, we may try to connect our work with preemptive semantics or the verification of multi-threaded program. Okay, that's all. Thanks for your attention, and I'm ready to take questions.
We have time for a couple of questions. Okay, let us kick us off. So thank you very much for the accessible talk, even though I'm not an expert in the field. I liked your examples very much. So one question that popped to my mind is, so you had this example where you had I, and then on the stack, the next variable was pi, okay?
Yeah.
And then you passed the pointer to I to the other thread.
Yeah.
What happens if the other thread actually changes the pointer and just says pointer +1 and then starts to modify this? Then this should no longer be private, but so how do you deal with that?
It's actually, sorry, I'll get to it. It's, yeah, I think this is. So as you just said, it can be some bad things when the colleague here changes the variable of j by using some bad pointer arithmetic. So that's why we need to verify it can provide the guarantee. So as I just said, the compiler correctness depends. It has an assumption that the colleague does not do some bad stuff like you said. So of course the compiler correctness, again, the compiler correctness depends on the counterpart does not do some bad stuff. That's it. I think it's mainly. So if possibly you get some assembly code that actually does these bad things, and in that time you are not able to verify it to be composed with a compiled program. Yeah, that's it.
I see. Thank you. Are there questions from the audience for people who are more qualified than me to ask questions? No. All right. Cool. Thank you very much. I think that's very exciting work. Thank you. Okay. And the next talk will be by Shufan, who will be talking about link time optimizations, particularly of dynamic cast. So take it away.
Okay. Thanks for the introduction. There has been a long-standing C++ folklore that says RTI and Dimecast are horrible. And if you search online, you will find plenty of posts complaining about them. And sometimes they even make fun of them. That's how much they hate them. Right? But is that folklore true? So today I want to get to the bottom of this folklore. And more importantly, can we dramatically reduce the overhead of RTI and Dimecast using link time optimization? So first, let's look at what Dimecast actually is. Dynamic cast is a handy feature that in C++ that allows us safely convert the pointers or reference between types. For example, let's see we have class dog, cat, and bird, and they all inherited from its base class animal. If we want to know that if the current object can fly, we can use Dimecast to check if the current object is instantiated from class bird. So what's nice about Dimecast is it is type safe, which you don't risk casting to the wrong type. And it helps us keep the code readable and maintainable. But here's the catch. The Dimecast works at runtime, and it depends on knowing the class hierarchy. So that leads to a big question, which is, how does a program know the type information in the runtime? And where does that type information come from? The C++ uses something called runtime type information to keep track of the type information during program execution. In this example here, the compiler generates RTR data for each class in the hierarchy. Each RTR data has two important pointers. One pointer points to its type name string, and another pointer points to the RTR data of its base class. At runtime, if we want to get the RTR data from the object, we start by looking at its virtual table. And the pointer of the virtual table actually is stored in the object layout. And from the virtual table, we follow the RTR data pointer to the RTR data. And from there, we know exactly what type the object is. Once we have understood the class hierarchy that is represented by RTI, we can go ahead with the Dimecast algorithm. Roughly speaking, we can think of the Dimecast algorithm as a depth-first search. So let's see we have an object that is instantiated from class D. And now we want to Dimecast it to the class B. So we start by looking at the class D RTR data. But since the class D is not the type that we are looking for, so we follow the inheritance chain upward. And eventually we reach the class B. So now we have found a match. And that means the Dimecast successes, and we get a valid pointer with type class B. So, but here is the downside. RTI is kind of infamous for eating up space. For one thing, each RTI data takes at least 24 bytes. And this is just a start. The type name string that it stores can be super long, like way longer than what you would expect. This is an example that is pulled from Chromium project. And the type name string itself is already 375 bytes. So now imagine that kind of overhead spread across 45,000 cars in Chromium. It adds up really fast. So now you can see why that folklore exists and why there are so many people hate Zen. Besides taking up space, the Dimecast also slows things down. There are a few reasons about that. The first is the Dimecast is implemented in the standard library, so calling it might cause the instruction cache misses. The second is, since it is a function call, so it acts like a barrier for the compiler optimizations. And most compiler optimizations, they cannot really kick in. And the third is the actual algorithm of Dimecast is depth-first search, which is a linear time complexity. So Dimecast is safe, but it is definitely not cheap. And most programming language, like especially for the C++, they try to stick to the zero overhead principle. It basically says two things. The first is you don't pay what you don't use. But in reality, most RTR data, they get generated even if your program never uses it. And that's wasted space. And it totally breaks the spirit of zero overhead principle. The second is what you do use is just as efficient as what you could reasonably write by hand. But Dimecast doesn't hold up here either, because it is way slower than handwritten one. And we will show exactly how it slows things down in our evaluation results. So both RTI and Dimecast, they are not good. But if the compiler is supposed to be the main tool for squeezing out performance and the space for the program, why can't it just optimize them away? We found this because that in the real world C++ projects, most classes are scattered across files. And with the per-file-based compilation, each file gets compiled on its own. So the optimizer cannot see the full class hierarchy, and it also has no idea if this class hierarchy is inherited or not inherited from outside. So because of these uncertainties, it has to play it safe and assume the worst case across files, which really limits how much it can optimize. So we use link time optimization. With link time optimization, each source file first compiled to its intermediate representation. And then the linker put all these pieces together into a big LTO module. So now optimizing inside this big LTO module gives the optimizer a much bigger view, which now it can see the full class hierarchy. And because the linker also performs the symbol resolution, it can also figure out if the class hierarchy is inherited or not inherited from outside the LT module. So once we have the full class hierarchy, and we know that the class hierarchy cannot be inherited from outside the LTO module, we came up our new link time optimization, which optimized the dynamic cast into the simple membership check. For example, if we are trying to dynamic cast to the class B, actually it will only work for the objects that are instantiated from class B or class T. So that means at runtime, we just need to check is the dynamic type of the current object class B or class T. If yes, great, we return the cast pointer. If no, we return the null pointer. So it's a pretty straightforward idea. And so now let's implement it into the compiler, which instead of calling the dynamic cast that is in the standard library, we have the compiler generate the simple instruction sequences to do the membership check. So in our implementation, the compiler first arranges the class the classes in the class hierarchy using a pre-order traversal. And then the compiler generates instruction sequences to transform the dynamic cast into the membership checks. But sometimes we might have to check a lot of candidates. For example, here there are 3 candidates can be casted to class B. And our investigation also shows that for some dynamic casts, there can be over 15 candidates. So checking them one by one is not efficient. But thanks to the pre-order layouts, we can simplify each membership check into comparing their lower and upper bound in the layout, which gives us a constant time complexity. Besides optimizing the dynamic cast, we also want to cut down the space that RTI takes up. So first, we analyze the liveness of the RTI slot in the virtual table. And then we prune the slots that are never used. And once the dead code elimination optimization kicks in, all that unused RTI data get cleaned out. So now we have worked through our method. Let's see how it holds up in practice. To evaluate our benchmark, our optimization, we built a benchmark with over 50 million lines of code, which include both typical C++ project and the large-scale ones. But many large-scale projects, they disable their dynamic cast or use the custom RTI system. For example, Chromium, LLVM, and V8. So for these projects, we replace the custom RTI system with the standard dynamic cast. And we also evaluate our optimizations under 2 main types of link time optimization, which is full LTO and thin LTO. The full LTO is a heavier and more aggressive version that we talked about earlier. And the thin LTO is a lightweight alternative, which it is scalable and it can build fast. So it also has been the default LTO build for the Chromium project. So now let's look at the evaluation results. So we saw runtime performance improvement on all benchmarks in the full LTO. And on average, we achieved 1.4% performance improvement. especially for the Solidity smart contract compiler, we got over 5% speed. And our optimization also cut down the binary size across the board. And on average, we achieved 1.7% code size reduction. And especially with the Envoy project, we reduced the code size by more than 4%. Now to see how well our optimization works on the large-scale projects, we picked LLVM. LLVM is a project that is heavily relies on the dynamic cast. And, but to avoid the performance hit from the dynamic cast, it builds its own custom RTI system. The upside is it is fast. But the downside is it is not compatible with the standard dynamic cast. And it also requires a lot of manual code. For example, if you want to add a class into the LLVM, you need to implement the class of method. And you also need to create a new unique class ID. And even worse, LLVM only uses 1 byte to represent that class ID, which means if the code base grows or get refactored, there can be some compatibility headaches. So we replaced the LLVM's custom ITDI system with the standard dynamic cast. And the result is really brutal. It costs a 315% performance regression. So now more than 3 times slower for C++. That's a lot. And then we applied our optimization. And now we dropped the slowdown to around 5%, so which is a huge improvement. And now let me wrap up with the key takeaway. So based on our study, the folklore about RTI and dynamic cast are true. And they are one of the few C++ features that violate the zero overhead principle. So what did we do? We broke that folklore using our link time optimizations, which we restore the zero overhead principle for them by applying our new link time optimizations. For one, we optimize the dynamic cast performance to match that of handwritten ones. And we also get rid of the unused RTI data, which now you are not paying space you don't even use. It's a step toward making C++ safer and faster, and without sacrificing the power it gives developers. Thanks for the listening.
Thank you very much. Really interesting project and talk. I guess I just wanted to check about the applicability of this. With link time optimization, am I right that this really only works when you have a full statically linked binary you want to run? And for example, if you have a binary that's going to work with shared object libraries and things, this doesn't apply. Yeah. Is that correct?
For the link time optimization, if you have the full project and you can get all of the source code and you build them together, then you can get a giant LTO module. Then you can analyze the.
But for example, I build tooling on top of LLVM, and I typically have the LLVM parts loaded as a shared object library. Could I apply LTO to that .so file?
Actually, in the dynamic linking, it doesn't work, but because our LTO module is only if the class hierarchy can be referenced by the shared library, then our optimizer cannot kick in.
Yeah, okay.
But if your project is really care about the performance, you should put the LLVM source code into your project and build a large LTO module. Then our optimization can kick in.
Makes sense. Thank you.
Hi, I'm Singyun Nam from Seoul National University. Thanks for the great talk, and I really like the idea that you can optimize away the RTTI overhead by compiler optimization. But I have a question. So, in order for this optimization to work, I believe that the distance between where the class is actually specified. So, for example, you like create a object of type D, and the place where you actually do the dynecast for, so for example, from type A to type D. So they should be really close, or maybe like one function call away, because otherwise, in order to be sure that you can actually optimize the dynamic cast, you have to probably inline 3 or 4 function calls into that code. So how did you get to mitigate that issue? Or like, does it actually even work if the dynamic cast is like 3 or 4 functions away, or maybe more, from the actual class instantiation?
Sorry, could you repeat your question?
Oh, okay. So what could your optimization do if if the point of class instantiation is probably far away from the dynamic cast?
You mean you have a class and you want to dynamic cast into another class, and
if the function call depth from the point of instantiation to the dynamic cast is far away, so maybe you require several function calls, then I believe you cannot inline all the function calls into, so that you can be sure that you can optimize the dynamic cast from one type to another.
Yeah. If there's there are many function calls, then actually the inliner will inline all of these calls if it is good to inline.
So you actually do inline all the function calls?
Yes. Actually, yes. You can also regard it as we know what dynamics do, and we inline it into our code and we optimize it.
Cool. Right, and then let's do one last question.
Hello, is this, yeah, okay. Very cool work, thank you. My question is about the compile time overhead of this, because if you can only do this at link time, like you've got, LLVM is enormous, right? If I'm trying to compile LLVM, this already takes a ridiculous amount of time. If after that I have to gather up all of the object files and then go through and analyze all of the class hierarchies, how much time, what am I actually paying at compile time to get these performance benefits?
As for the compile time, actually, it depends on the link time optimization type. For example, in the full LTO, which is a monolithic link time optimization, we will get because it is not scalable. So before our optimization, it's when we compile the Chrome project, it takes 4 hours, and then apply our optimization until you need to pay more, 10 minutes. It's it's not too much, but if you but currently that actually the single LTO is the more is the better option, which it is non-scalable. So we evaluate a little bit the compile time. The compile time overhead is less than 2%.
So this is the overhead over once you're already doing LTO.
Yes.
But if I compile this thing without using LTO versus using LTO so that I can do this dynamic cast optimization, do you have some insight on how much worse that is? How much slower that is to compile?
I think it depends on your project, how large your project is, and how many cores in your computers. For example, a single LTO it can be parallel linking. It supports parallel linking. So if your computer has a lot of cores, then it can parallel linking many tasks. So I think the build time will not increase a lot. But if you use full LTO, yeah, it's maybe your compile time will be doubled or tripled. It's not good.
Okay, all right.
Great, thanks. We will thank you very much for the talk and the engaging discussion. And let's switch over to the next speaker, and let's thank the speaker again. The next talk in this session is going to be by Dong Wei, and he will talk about testing of shader compiler backends.
Hello everyone, I'm Dong Wei Xiao from the Hong Kong University of Science and Technology. And I'm happy to share our work on divergence testing of graphic shader compiler backends.
So could you turn off the night light? Because like,
oh,
yeah, yeah.
How can I turn it?
So it's Windows.
Can you use this one?
Could you go to settings?
Yeah, sure.
Yeah. Display maybe. Or just search for night light. Yeah, yeah. Go there and turn off. Yeah.
Thanks. And this is the joint work with Professor Zhendong Xu from ETH. Graphic shaders are used in a wide range of applications, including gaming, AR, VR, and also building information systems. Graphic shaders are typically written in high-level DSLs, such as GLSL or HLSL, and those DSL programs are compiled by the graphic shader compilers into GPU executables. But the graphic shader compilers can be buggy, and those bugs can affect downstream applications. For example, you may get unexpected output images in your gaming, and that will affect the user experience or even causing confusion. Let's use a simple shader program to illustrate the concept. So in this program, the program aims to draw a ball inside on a screen. The program takes as input the coordinates of the ball and also the pixel on the screen that it wants to draw. The program sets the radius of the ball and also the 3D position of the camera in the space. The program then computes the distance between the camera and the center of the ball. If the distance is less than the radius of the ball, it means that the camera is inside the ball. And in this case, we set the color to be a background color of black. Otherwise, the program will continue, and it will shoot a ray from the camera in the direction of the coordinates in the pixel. It then computes how far that ray can travel before hitting the ball. If the distance that the ray travels is greater than 0, it means that ray hits the ball. And in this case, the program computes the color based on the hit point of that ray on the ball. And suppose we get a purple point on the screen. Otherwise, it means that the ray doesn't hit the ball and instead hits into the void. So we set the color to be a background color of white. By executing this program on all the pixels on the screen, we can obtain the image that we want to draw, which is the ball on that you see on the screen. Graphic shaders are almost executed on GPUs. So GPU has a unique pattern. They are composed of different execution units. Each execution unit will launch multiple threads simultaneously to execute the same shader program and with their individual inputs and obtain the outputs. So in this case, the inputs to the GPU threads are actually composed of different kinds. So we have one kind of shader inputs, which is called the uniform inputs, like the center of the ball. So why do we call them uniform? Because for those inputs, their values are consistent across all the GPU threads. But we also have another kind of input, which is called the varying inputs or divergent inputs. For those inputs, like the coordinates of the pixel on the screen, their values may be different across different threads. But GPU has a unique pattern. They enforce that every thread in the GPU should execute the same instruction in every lockstep. And this pattern is typically called the single instruction multiple threads pattern, or for short, the SIMT model. But this unique model may bring unique challenges to the graph-shader compiler developers because those patterns are really different from traditional CPU programs. So why do we say that? We also use this example to illustrate how the GPU threads execute under the SIMT model. So suppose we have three different GPU threads, thread 1 and 2 and 3. So for the first two threads, their corresponding rays hit the ball. But for the thread 3, its corresponding ray doesn't hit the ball, but instead hit the background. So at first, all the threads will execute line 4 to 7 because there's no diversion and because there's no branch here. And then they encounter line 7, which is a branch, and there's a branch branch body. So this branch is kind of like a uniform branch because all the threads will either execute this branch or not. So basically, the truth value of the if condition will be consistent across all the threads. So because in a typical because the distance is either less than R for a particular camera and ball or greater than R. And then they execute line 11 to 13 as usual. But next, they encounter a different kind of branch, which is called divergent branch. So for this kind of special branch, the thread may hold different truth value for the condition of this kind of branch. And for thread 1 and 2, since their rays hit the ball, they should execute the if branch of this kind of branch. But for thread 3, they should execute the else branch. So there's a dilemma. So which branch should the GPU execute? Remember that the GPU enforced that every thread should execute the same instruction in a single lockstep. So what the GPU does is that it decides to execute both branches and ensure the correctness through a set of tricks. So what kind of tricks do they use? So for thread 1 and 2, since they should enter the true branch, their status will be set to be active. But for the thread 3, since it shouldn't enter the true branch, it will be set in an idle state. An idle state doesn't mean it doesn't execute instruction, but instead it will execute instruction and mask all the side effects out. A side effect can be a memory or register wise, and those effects will be masked out so that the state of the thread 3 won't be affected by entering the true branch. And the mask is managed by a special register called the execution mask register. And this execution mask register is kind of like inserted by the compiler to handle this. Now, after executing the true branch, the thread 1 and 2 will receive their respective color, while the color of the thread 3 won't be affected because it is masked out by the execution mask, and the side effects are not effective. Now the GPU will execute the other branch, and when executing the other branch, thread 1 and 2 will be set to be idle because they shouldn't enter this branch, while the thread 3 will be set to be active. And so the thread 3 will receive the color of white. Since the thread 1 and 2 are idle, their previously set color won't be affected. So that each thread will receive their correct color by the end of these two branches. And now we come back to the compiler, and what does compiler do in this setting? So compiler is made up of three parts: the front end, middle end, and back end. The front and middle end are responsible for hardware-independent optimizations like constant folding and simple optimizations. But for the back end, they are different and complex, they are bound to the GPU features. And as we will see later, the backend optimizations are kind of really different from the CPU backends. And they have special optimizations like execution mask insertion, which doesn't exist in the CPUs. They also have, for the other optimizations like instruction scheduling, they also need to take into account the features of the GPUs. And our work aims to test the backend optimization bugs. So why do we want to test the backend instead of focusing on the other whole pipeline? Because we think that the backend is unique and interesting. It is bound to the GPU features, and the GPU features the same team execution model. The backend of the shader compilers are also pretty complex, and sometimes even as high as 3 times of code size at the front and middle end combined. And this is different from the traditional CPU programs. And graphics shader compiler backends are also heavily invested because they are kind of like the secret weapons of the competing GPU vendors. And we found that there's not enough works on focusing testing the graphics shader backends. And GPU graphics shader backends are also pretty hard to test because they are last stage of the shader compiler. And if you want to trigger interesting and diverse optimizations, you need to have to go through the first 2 pipeline stages in order to reach the backend. And that is pretty hard to like diversify the behaviors. And sometimes the developer think that the backend optimization bugs are kind of like a long-standing problem according to a preliminary survey of the existing bugs on the backends. So the question is, how can we effectively test the compiler backends? Now, we can first think about what are the commonalities of those backend optimizations. That may inspire how we design the test case generation problem. And we find that our observation is that backend optimizations are heavily affected by the divergence issues we previously mentioned. Why is that the case? We've taken a look at two optimizations at the backends. For example, for the execution mask insertion at the backend optimization, it inserts the execution mask and handles the correctness of the divergence and uniform branches. But even this task is not easy. The compiler needs to analyze the control and data flow to decide the divergence of each variable and each conditional if branch. For example, at line 7, the compiler needs to decide that this line is a uniform branch because the D and R are kind of like a uniform variables through analysis. And then it avoids inserting the execution mask because it will incur extra overhead during runtime, and instead resort to the traditional and ordinary branch instruction. But for line 13 to 18, it is different. It is a divergent branch, and different threads may should have executed different branches of this if statement. So it should handle this through the execution mask. For example, it decides to insert an execution mask setting at the front of the branch, and then revert it when executing the else branch to ensure that those branches who should execute the else branch will receive their correct values. And later, when exiting the branches, the compiler will unset the execution mask. And also, it also affects the register allocation because in GPU, there are 2 different sets of registers, like the scalar registers. For those registers, the values are consistent for all the GPU threads. But there's also another kind of registers, which is called vector registers. And each thread will have their own copy of the vector registers so that they can hold divergent values, which are values that are not consistent across the GPU threads. So in this case, the compiler needs to analyze the divergence, whether a variable is divergent or uniform through the control flow and data flow analysis, and later decide that they can allocate the variable D, which represents the distance between the camera to the center of the ball, to the scalar register files. But for the other registers, like the coordinates, the compiler needs to allocate them to the right registers because the coordinates of the pixels may vary across different threads. So, basically, let's come back to the question of how to effectively test the compiler backends. We think that the divergence is the key to unlock the various backend optimizations. And to that end, we generate the programs with various divergence patterns as testing inputs for effective testing. Now here we briefly show our pipeline, which composed of majorly 3 components. First is the program generation, which is aware of the divergence status of each statement of an expression. And this component aims to stress test the control flow divergence patterns of the compiler. And then we perform the liveness mutation, which aims to stress test the data flow divergence of the compiler. And later, we compile the generated and mutated programs and execute them on multiple GPUs to cross-check the results. Any inconsistency in the outputs indicates a logic bug. We also find crashes, which doesn't produce an output and instead produces some crashes. So we use this example to briefly show that our divergence-aware generation is effective. So in this case, we need to generate statements that are interleaving the uniform and divergent expressions. And this box triggers an AMD compiler to hand. If we instead generate programs that are either all divergent for all statements or either all uniform for all the statements, then this bug won't be triggered. But we observe that if you randomly generate programs, you can easily lead to those 2 cases, which is either uniform or either all divergent. How do we do that? So we basically maintain a probability to sample from, which you can customize by yourself. And then we generate, our statement generator will only generate statements that respect the divergent and uniform properties. And then we maintain a divergent context for effective inference, like maintaining the variable status. Like for example, we generate a uniform variable, which was put it in the uniform bank, and we generate a variant variable, we put it in the divergent variable context, and so on. We continue this process, and And later, we also perform liveness mutation, which kind of like extends the liveness of variables. For example, initially we defined the variable c at line 4, and later during the mutation, we extend the use of c at line 10, which kind of like complicates the data flow of the program. And by complicating the data flow, we make it more interesting divergence patterns. We test our programs on 4 state-of-the-art GPUs, including Intel, NVIDIA, AMD, and ARM. And we also we found 12 backend bugs across those GPU vendors. As a byproduct, we also found 2 bugs that are not in the backend. And we've showed that our individual components contribute reasonably to our effectiveness. And if we randomly generate programs, your effectiveness will be pretty poor. And we'll compare with existing works, which GeoFuzz is acquired by Google, and FTrader is our previous work. And those 2 works are not targeting the backend compiler, and we find much more backend bugs than them. So we come back to our previous observation that the divergence is the key. And we show this by showing that we actually improve the coverage on individual optimizations by pretty much a significant amount. So to conclude, we are the first to test the backend optimizations in graphics shader compilers, and we generate programs with various divergence patterns. And we found 12 bugs in 4 compilers and outperform existing works. Thanks for listening. I'm happy to take questions.
Are there questions?
Thanks very much for the lovely work. I'm Alistair Donaldson from Imperial College London. GL Fuzz was my project. I'm delighted to see shader compilers at PLDI. That's excellent. When we were doing GL Fuzz, a big problem we had was comparing results between GPUs when floating point is involved, because the floating point rules in GLSL are very relaxed.
Yeah.
It looked from your examples, are you restricted to integers for your testing?
Yeah, exactly. We also tried floating points initially, but after reporting some bugs, the developer deemed that, okay, it is natural and unavoidable, so we just disable them. Yeah.
Okay, and I wondered also what you do about integer undefined behavior, like avoiding divisions by 0 or avoiding those sorts of undefined behavior.
Oh, we take inspiration from your work, the undefined avoiding undefined behavior in shader compiler, which is like using math wrappers to post-transform the programs. Yeah.
Cool. Thank you.
Thank you very much. I think let's move on to the last talk of the session, and thank Yongzhang again. Okay, and then the fifth and last talk of the session will be given by Bonjour. And he will be talk about using fuzzing for continuous translation validation in compilers.
Check. Working? Okay. So my name is Bong Jun. I'm happy to here to present my research work, optimization-directed compiler fuzzing for continuous translation validation. So the problem we want to solve is the correctness of compiler optimization. A wrong compiler optimization can silently change the meaning of your code, leading to miscompilation. This is a very serious issue because in this case, a compiler does not give you warning. A compiler does not give you crash, so you not notice something bad happened immediately. So it's crucial to guarantee the correctness of compiler optimization in the first place. So give you the idea of what a miscompilation looks like, let's take an example. This is a source program. It divides a number by b and times b. And if a wrong optimization kicks in, it can cancel out b term, but we know this is a miscompilation because if we give an input 4 and 3, the source program would give result 3, and the target program would result 4. But by compilation, the semantics is supposed to be preserved. But the challenge here is the complexity of real-world compilers. A real-world compiler like LLVM has a really massive code base and is constantly evolving. There were more than 30,000 commits and from 1,000 of developers in 2024. And if you look at this graph, there are increasing number of optimization suggestions in LLVM. It means that more and more optimizations are getting added to LLVM compiler, and our job is to check the correctness of every single one. The current approach to solve this problem is to use translation validation. Translation validation checks if the source program and the target program are equivalent, and it's widely adopted in compiler community like LLVM. For example, if you want to add an optimization rule in LLVM, you have to give the TP proof in the PL, so there is no counterexample in the optimization. So if you have an optimizer with a source program, you'll get a target program by a compilation, and what TV does here, it checks the result of the source program and the target program, and they are equal for every possible input. So from the previous example, what TV does here is checks the equivalence of the source program and target program. It finds the counterexample automatically for you. But TV also have a limitation. It needs input program to find a miscompilation bug. So if you miss an input program to trigger the bug situation, you're going to miss the bug. So our idea is to design a directed fuzzer specifically effective for compiler optimization to automatically generate input programs. So our contribution is summarized as follows. We developed the first directed compiler fuzzer for LLVM and turbofan. We reported 27 miscompilations in our benchmark, while other state-of-the-art compiler fuzzers failed. And we reported 56 LLVM bugs, and 22 are patched as of today. So this is our system overview. We start with compiler source code with target location and initial seeds. And through slicer, we get a slice control flow graph and call graph. And using the information, the seed scheduler realizes selective coverage feedback and focused mutation target. And finally, the targeted mutator and compiler optimizer generates optimized program with a mutated program. And with translation validation, we can automatically find miscompilation bugs. So the first step is to identifying the target optimization. The target identification process is inspired by our observation that optimization is typically consists of two parts. The first part is checking the optimization condition, and the second part is returns optimized code. And the target line here, because the directed fuzzer's job is to generate an input program that reaches the target. So target line is where optimization is actually triggered and returned. So for example, if there is an LLVM commit, there will be updated source code. You'll notice there is a part that checks the optimization condition, and there is a part that actually returns optimized code. And this is going to be our target line. And because optimization has a really simple pattern, just like I said, we can do automatic target line collection. Like we can just do simple string search with a simple Python script. We can collect all the lines that returns a new optimized instruction. Or we can just prompt engineer LLM to analyze the source code and collect all the interesting optimization triggering lines. The second part is to use the guided search strategy. Guided search strategy through slicer and seed scheduler. The slicer is for selective coverage feedback. Coverage feedback is an essential information to guide the fuzzer. And if you can imagine, if we only use the relevant program locations in the coverage, we can boost efficiency. So this, for example, this is a CFG of our optimizer. And this is going to be the seed pool of our directed fuzzer. And as you can notice, there is a red part and there's green part. In red part, there's no way to reach the target optimization, but in the green part, the blocks are reachable to the target optimization. And in the seed pool, there are going to be some input programs that covers the red part, but you can imagine the input program that covers the red part, the blocks are not reachable to target optimization, and this is going to waste space in the seed pool. And there are going to be green programs that covers the green part in the CFG, and the covered blocks can reach to the target optimization, so we want to only keep the green part. So what we want to do here is to slice out, it increases the efficiency. What we want to do here is to slice out the red part in the CFG to only keep the green input programs in our seed pool. And seed scheduler uses distance metric. The basic idea of distance metric is assign distance to target values to nodes in the slice CFG. So this is the CFG that we got from the previous slicer. And we are going to assign distance 3 to the first block because this block is 3 blocks away from the target optimization block. And 2, 1, 0 because following the same logic. And what we want to do next is to generate more mutated programs for a closer seed. So for example, if a seed only covers the first part, because it has the greatest distance, we are going to generate only few input programs. And if a seed program covers all the part, and you can see it covers the block of the distance 0, we are going to generate more mutated programs. So what it does is that we are going to generate more input programs that actually triggering the target optimization more frequently. the last step is to use targeted mutation strategy through a targeted mutator. So interesting observation we use here is that it's not just conventional fuzzing. The input is a program. So in conventional fuzzing, the input is a bit stream. Because it is a bit stream, it's really hard to analyze the structure of the input. It's just a sequence of 1 and 0s. But in compiler fuzzing, the input is a program. And because this is a program, it has a really useful structures like control flow and diffuse we can use. And diffuse relation is extensively used in optimization. Because optimization typically checks the diffuse relation of a program to actually apply optimization rule. So for example, if we have this optimization rule, this optimization transforms a program from a source program that multiply by 2 to the c to shift left by constant c. If ever this optimization rule is implemented in an optimizer, the first check is going to be to identifying the multiplication operator. And next check is going to identifying the first operand and check it is a variable x. And next, we are going to check the second operand is a power of 2. And finally, the optimization is going to return the optimized program. So using this observation, we can implement a really efficient strategy that finds the next mutation target. Let's say in the input program, there is an add instruction. And let's say mutator changed the add instruction to the multiplication instruction. And it's going to increase the coverage because the first check in the CFG was the identifying the multiplication operator. And if you look at closely the neighbor nodes, there is a x and y nodes. And if you look at the CFG of our optimizer, the next check is about the nodes x and y. So using this observation, if we mutate more the neighbor nodes, we are going to cover faster the next optimization condition checks. So let's move on to the evaluation section. Our Optimus framework consists of 2 parts. The first part is the fuzzer, and the second part is the translation validator. For LLVM, we implemented our own fuzzer, and we used a LLVM translation validator. And we collected all the 24 miscompilation bugs for the past 3 years in the LLVM. And if it's detectable by a LLVM translation validator, and we compared the other state-of-the-art compiler fuzzer like Flux and LLVM mutate. And for Turbofan, we implemented our strategies on the existing JavaScript engine fuzzer fuzzily, and we used TurboTB translation validator, and we used the known miscompilation bugs appeared in TurboTB paper. And we compared our fuzzer to the knife fuzzily. And we assessed effectiveness of our framework. It appeared really, it performed significantly better than other sort of fuzzers. It reproduced 23 cases, while other sort of fuzzers reproduced nothing within an hour. And for Turbofan, we reproduced 4 cases, while other fuzzers did not reproduce anything. And we did evaluation study on strategies effectiveness. On LLVM, we implemented 3 variants. The first variant is base. This is an undirected fuzzer without any strategy. It only has just mutator operator we implemented. So in the base case, only a few cases are reproduced. If you see the top line is at 60 because the timeout is at 60 minutes, it means that the reproduction has failed. And with guided search strategy, the effectiveness really improved. The reproduction time reduced a lot, and we reproduced a lot more cases. And with the targeted mutation, the reproduction time also reduced, and we reproduced 1 more case. And same thing for Turbofan. We implemented 3 variants. The base fuzzer does not reproduce anything. And with guided search strategy, it's significantly better. The reproduction time reduced also, and with targeted mutation, we produce 1 more case. And you can see the reproduction time reduced also. We applied Optimus to LLVM bug finding. Optimus appeared to be a really effective tool to find unknown miscompilations. We deployed Optimus in 2 different modes. The first mode is a continuous mode. We applied Optimus for every target in each LLVM update, and we applied Optimus in batch mode. We applied Optimus for all targets in the latest version of LLVM. So in continuous mode, we found 8 bugs from LLVM GitHub commits. So let me illustrate what we did. So from an LLVM GitHub commit, there will be a updated source code, and we analyzed as I described. And from the target line, we used Optimus to find miscompilation, and on with the same process. And in batch mode, we found 48 bugs from the latest version of LLVM. So for example, if there is a source code like inst-combine select .c++, we analyze source code automatically to find the target lines, and we fed the target lines to Optimus one by one, and finally found 48 bugs. So in summary, we developed the first directed compiler fuzzer using a continuous translation validation. We developed 2 strategies. The first one is guided search strategy with selective coverage feedback with distance metric, and the second one is the targeted mutation strategy that effectively find the next mutation target. So, and we also have a real-world impact. We reported 56 bugs to LLVM, and 22 are patched as of today. Thank you for listening. You can find more details in our website.
All right, we have time for a couple of questions.
Hi, hello. Really cool work. I have a question. I see you have found some bugs in inst-combine for new commits on inst-combine. My understanding is that you're supposed to still have a live link to actually check that the optimization is correct or not. Does that mean that the problem, the bug you found was the mismatch between the implementation of the optimization and the alive link that you have to check that it's actually correct?
So I missed the second question, sorry. The first question was this framework depends on the translation validation tool we use, right? So for TurboFan, we use TurboTV, for LLVM, we use Alive. So it is kind of bound to the bugs that can be detectable by the translation validation tool of our choice. And Alive tool is a bounded translation validation tool, so we can miss some loop related miscompilation. That is true.
Okay. I see. Thanks.
Hi. I noticed that you did say that in the PR. Can you introduce yourself? Hi, Hamir Abbasi from Quantsite. I did notice that the existing translation validation tool is already run in the PRs. So because of this, are you not selecting for bugs that would not have been caught by those translation validation tools in the first place? Specifically, did you try running this on commits that actually found bugs and those that didn't find bugs in the existing translation validation tools?
So the main limitation of how the translation validation is used today is that the human developers are writing their test cases to fit to the translation validation tool. So even if they're trying really hard to cover all the cases that optimization rule covers, there were cases that they're missing. So our fuzzer is really excels at generating the missing parts of the optimization rule covers, and I remember many cases that we caught the bugs like that. Did I answer your question?
Yes, it does. Thank you. Okay, then let's thank you again for the great talk. And this concludes this interesting session. There will be lunch now, and then the remaining last sessions of PLDI.
Welcome everyone to the databases session. I'll be your host. I'm Adam Chapala from MIT. And our first talk will be on solving satisfiability problems for SQL queries. And the speaker is Pinhan Zhao, who I believe is thinking ahead and looking for an internship for next summer, if you'd like to ask him about that afterward. And without further ado, over to you.
So, hello everyone, my name is Pinhan, and I'm a PhD candidate from the University of Michigan. And today I'll talk about general symbolic reasoning engine that uses the idea of AND approximation to reason about complex SQL queries. So in our work, the core problem we study is how to automatically generate an input for n queries such that their output on the generated input satisfy a given application property. So this can be instantiated to solve many different real-world tasks. Let me give you 2 examples. And for instance, one task is to disapprove the equivalence of 2 queries. In this case, we want to find an input such that the outputs of 2 queries are different. And this is particularly useful for rewrite validation. As modern database systems like Calcite and MySQL rely on rewriting to optimize query performance, it is critical to ensure that the rewrites are correct by checking if the rewritten query is semantically equivalent to the original one. And if they're not, we want to generate a counterexample to help the developer identify and fix the issue. And equivalence checking is also useful for automated grading. And in this case, it allows us to automatically check the user solution matches the ground truth query. And if it is wrong, provide a counterexample to illustrate the user's mistake. And another real-world task is clustering a set of queries. So here, the goal is to find an input that can divide n queries into 2 sets, where queries in the same set produce the same output, and queries from different sets produce different outputs. And this is especially useful for disambiguating synthesis or generic queries. For example, when a program synthesizer or a language model returns multiple queries, we can automatically group them based on their behavior and identify semantic differences to help the synthesizer further refine the solutions. So there's prior work that tries to solve some instantiations of our problem. For example, equivalence checking for 2 queries. So let me briefly discuss them here. So broadly, they fall into 2 categories. First, we have fuzzing techniques for SQL. Tools like EvoSQL, XData, and DataFiller adopt this approach. These methods are cheap and can quickly produce many test cases. However, because they generate inputs by considering no or very little semantic information, they often miss the specific inputs we care about. And the other line of work uses symbolic reasoning method. For example, VARIEQL, COSET, and QEX use symbolic techniques to reason about queries. These methods are complete, meaning that, in theory, they are guaranteed to find a desired input that meets the problem's criteria, if there exists one within the given input space of interest. But this completeness comes at a cost. They are often very computationally expensive, especially for large or complex queries. So our approach also uses symbolic reasoning method, but in a very lightweight manner. So rather than reasoning about the complex semantics at once, we try to break down the challenge and consider the SQL semantics in a way that is lightweight without hindering the completeness. So in this way, we aim to combine the best of the both worlds, fast and also complete. So now, before telling you about our key idea, let's start with a brief review of how prior symbolic approaches work. So typically, this method precisely encodes all possible input-output behavior of SQL queries in an SMT formula. That is, the SMT formula encodes the query semantics for all possible inputs, such that each input-output pair of the query corresponds to a satisfying assignment. However, the limitation of the approaches like this is that precisely encoding complex operators like join may lead to many possibilities, as there are exponentially many ways that the tuples from input table can be matched and joined, depending on which tuple pair satisfies the join condition. And this makes the formula very hard to solve. So here, we show one possible way that the join operator can behave, which is there's exactly one pair of tuples from two input tables satisfy the join condition and will be joined. However, precisely encoding the join operator requires us to capture all possibilities, which can be a lot and makes the solving very expensive. So this motivates our first key idea. How about we only consider a subset of them? Because a formula that encodes a subset of reachable behaviors can be faster to solve. Therefore, we propose polygon, which is what you get when you under-approximate a circle, which rhymes with sequel. So now, let me introduce polygon by first explaining the core idea behind our approach. So rather than tracking all possible query behaviors, which is often extremely expensive, we choose to track and encode only a subset of possible behaviors, which is an under-approximation. So by focusing on smaller subset and reasoning about an under-approximation of query behaviors, it brings out a formula that is often very fast to solve. So now, let's walk through a very simple random example to illustrate our approach. Consider this database with two tables. We have a faculty table with two columns, ID and name. And we also have a teachers table, which shows which professor teaches which course. And given this database, our task is to write a query to find all faculty who teach the course CS101. And the output table in this case will be like this, because Alice is the only professor who teaches the course CS101. So to ground our approach in a real-world problem, let's consider an sequence checking task with two queries. And here we have two very simple meta queries just for illustration purpose. And Q1 is the correct query. It first joins the faculty table with teachers to find which professor teaches which course. And then it further filters the result to only include the rows that the course is CS101. And finally, it outputs the name of those faculty members. On the other hand, Q2 is incorrect. It mistakenly looks for faculties who teach CS202 instead. And our goal here is to automatically generate input that can make the two queries produce different outputs. And now, mapping the two queries onto their abstract syntax trees, we can see that Q1 first performs an inner join and then projects the faculty names. And Q2 follows the same structures with a join followed by a projection. So now, I was talking about the concept of under-approximation for SQL. So how do we actually represent that, and what does it really mean? So now, let me first show you how to represent under-approximation in our approach. So each ASC node, which corresponds to a query operator, is assigned an under-approximation, represented as an array, possibly more than one dimension. And the query's under-approximation consists of the array for each ASC node of the query. And then for n queries, the under-approximation is described by a mapping M, which maps each ASC node of the queries to their under-approximation. So now, let me explain this in more detail. Let's start by understanding what the under-approximation actually means for a query operator first. Take the join operator from Q1 as an example, which corresponds to the ASC node named V2. So the under-approximation V2 is represented as a 2x2 matrix, where each element of the matrix is corresponding to a pair of tuples from the input tables. For instance, the top left element of the matrix corresponds to T1 from faculty and T3 from teachers. And each matrix element controls the join behavior of the pair of the tuples, which indicates whether the corresponding tuples satisfy the join condition or not. And each element of the matrix may take one of two possible values. If the value is T or true, it means the corresponding tuple pair satisfies the join condition and will be joined. Otherwise, if it is F or false, it indicates the tuple pair doesn't satisfy the join condition. So here, we have a concrete example of an under-approximation for this operator. And in this case, most pairs are marked F, while the value for the pair of T2 and T4 is T, meaning that in this under-approximation, it tracks the behavior where only the pair of T2 and T4 satisfy the join condition and will be preserved in the output. So essentially, this AND approximation represents one possible way that the join operator can behave, focusing on a smaller subset of all possible inputs. So this AND approximation for the operator can be encoded as an SMT formula, which encodes one particular input-output behavior specified by the AND approximation for this operator. Then, to encode the AND approximation for queries captured by M, we conjoin the encoding for each ASE node in the queries. And as a result, the final formula also captures only a subset of query behaviors. And finally, we append the property that states the output of two queries should be different. And if the formula is satisfiable, the model will give us an input database that meets our application property. So now, we have seen how AND approximations enable us to track a subset of query behaviors efficiently. But what we have done so far is assuming a specific AND approximation for queries. So here's the question. What if the particular AND approximation misses the behavior we care about? So to address this, our second idea is to define a family of AND approximations that collectively cover all behavior of interest, and then perform search within the family, therefore making our approach complete. So in this way, if one AND approximation doesn't capture any behaviors that meet the application property, we search for other AND approximation within the family until we find a desired one, or the search space exhausted. So I will then explain how to define a family of AND approximation. So to build the family for queries, we need to first define a family of AND approximation for each operator first. So now let's use the inner join as an example. Recall that in the matrix for inner join, each element corresponds to a pair of tuples and can take either true or false. So every AND approximation in this family needs to assign a value to each of these matrix elements. So for example, if both input tables have 2 tuples, then the output table may contain up to 4 joint tuples. This results in 2 to the 4th, which is 16 possible AND approximations covering all possible join behaviors of interest. And then to define the family for queries, we combine the family for each ASE node of the queries compositionally. And in this way, each AND approximation in this family corresponds to a specific subset of query behaviors. And with the defined family of AND approximation for queries, we are able to systematically explore different AND approximations using search. And during the search, it is clearly too slow to enumerate each individual AND approximation one by one within the family. So in our technique, we use the so-called conflict-driven AND approximation search that learns the conflict from unsatisfiable AND approximation and avoids similar root cause in the future to accelerate the search. And due to time constraint, please refer to our paper for the details of this part, and I'm also happy to discuss it offline. And finally, we have evaluation. And to evaluate polygon in real-world scenarios, we use over 30,000 benchmarks across 2 real-world tasks. And the first task is equivalence refutation, covering more than 24,000 query pairs from various sources. For example, one source is from LeetCode, where each benchmark is a pair of a user-submitted query accepted by LeetCode and a ground truth query. And the second task is query disambiguation, where the goal is to evenly split n queries into 2 clusters. And in our evaluation, we consider n is 50 and n is 100, giving us 2 sets of benchmarks, each containing either 50 or 100 queries per benchmark. And each benchmark is curated in a way that's guaranteed to be solvable. So we compared polygon against a wide range of existing approaches. We included symbolic approaches that precisely encode the semantic SQL queries, and we also have fuzzing-based approaches that generate test inputs for SQL queries with considering no or very basic semantic information. And our evaluation shows several key points about Polygon's performance. For the equivalence checking task with a 1-minute timeout, Polygon can refute over 5,400 query pairs. That's about 1.7 times more than the best existing approaches. So given that most query pairs are actually expected to be equivalent, this is a surprisingly high number. And in terms of efficiency, Polygon can solve the benchmarks with a median solving time only about 0.1 seconds. For the query dissemination task with 100 queries per benchmark, Polygon solved about 97% of the benchmarks within 1 minute. And the median solving time was about 18 seconds, whereas the best baseline solved only about 68% of them. It's also worth noting that these benchmarks were highly complex, with a median of more than 400 ASC nodes per benchmark. So this highlights the capability of Polygon of solving very hard tasks efficiently. And that brings me to the end of my talk. Thank you for your attention, and I'm happy to take any questions now.
Okay, questions. I think we have someone going to run a mic around to where the questions are. Any brave souls want to kick us off? Or I can take a shot at it. I noticed in the way that you're using these matrices to represent different under-approximation strategies that seems like there's probably a lot of symmetries there where there are different matrices that really represent the same idea. You can just like flip them around there, the diagonal or something, and it should be treated the same. Do you take advantage of those symmetries to speed up the symbolic operations that you perform?
Actually, I think I'm not sure if there's any symmetry because each element of the matrices or the array may correspond to different pairs of tuples from the input tables. So even though they are symmetric, they may be two different matrices. So
I was thinking of how it seems like for each of the tables that you're modeling, you should be able to permute it arbitrarily and not meaningfully change the satisfiability problem that you're looking at because there's no special identity of the elements in there. Is that not the case?
Can you explain how to like flip the tables?
So in general, we think of SQL tables as not even being ordered. So table with 1 and 2 as the values is the same as 2 and 1, but it looks like you're distinguishing those in the way you set this up.
Yeah, I see. Because we consider the operator like order by. So in that case, the ordering in the tables matters. So yeah.
Isn't the database engine allowed to reorder arbitrarily anyway? If you haven't asked for order by, you might get any order.
Yeah, because we use the list semantics, so we consider the ordering of the tuples in the table.
Okay,
yeah.
Thank you.
Yeah. Thank you.
We have a question over there. Get your steps in today.
Thank you. Yi Hong from University of Washington. So I wonder, what features of SQL you support? Is there any feature, any major feature you don't support in this project?
We currently don't support window functions like string operations, but we do support major features like drawing, order by, order drawing, the other common expression.
Yeah. I see. The other question I have is, it seems basically you decompose this problem into a series of under approximations, and it seems like they can be solved in parallel. Have you tried running multiple solvers on different under approximation?
No, we haven't tried that, but that could be an interesting direction to try in the future. Yeah.
Thank you.
Thank you.
Maybe we could get Yufei up here to plug in, and there's maybe enough time for one more question overlapping that operation. Where's Yufei?
I have a question about your matrix is mainly about projection and join. So what about other relational algebra operations? such as mapping from one to another?
Yeah, we have a different representation of the ender approximation for different operators. So like for a filter, the ender approximation is represented as an one-dimensional array. And for like joins, the ender approximation is a matrix. And the meaning of the ender approximation for different operators are defined differently. So basically, we have different definition and a different representation for different operators.
Okay, thank you.
Thank you so much.
Okay, thank you.
All right, so our next talk is going to be about teaching pointer analysis to understand database libraries, and we'll be hearing about it from Yufei Liang. And we should see his slides any second now. Okay, take it away, Yufei.
Good afternoon, everyone. I'm Yufei Liang, a first-year PhD student at Nanjing University. I'm delighted to have the opportunity to present our work, Pointer Analysis for Database-Based Application. In this work, we propose debug, an end-to-end point analysis framework for Java database-based application. It enables the construction of the value flow between Java application and databases. By applying debug to security analysis, we reveal 30 store XSS vulnerability and 3 broken access control vulnerability. Let's start with the background. We interact with database-based application daily, sharing on social media, shopping online, or posting on forums. This interaction generates massive value flows among users, applications, and databases. As a result, the data security becomes critically important. This raises 2 questions. Where does the data we receive come from? Could it originate from the malicious attackers? Where does the data we send go? Could our private information be leaked? To illustrate the potential risk behind the value flows, let's look at a real-world example of a store XSS vulnerability. This example is simplified from a real-world forum application. It consists of 3 components: an article controller that handles user web requests, a service that interacts with database via APIs provided by database frameworks, and a database with 2 tables, article and tag. The vulnerability is triggered in 2 steps. First, the attacker injects a malicious script into the database. In detail, the malicious data is embedded with an article object and flows to the persist API of the database framework. Then, the database framework generates 2 insert statements dynamically based on the API type and the points to relation of the arguments. During the execution of these statements, the malicious data is written into the database. Later, when a victim calls the find API to view the article, the malicious data is retrieved and executed in the victim's browser. This vulnerability allows the attacker to execute arbitrary code in the victim's browser. Such database-related vulnerabilities are widespread in production. For example, broken access control vulnerability and injection vulnerability are listed in OWASP Top 10 web security risks. To address it, we need tools that can capture the value flows between Java application and databases. Static analysis is well suited for this task. However, current static analysis face substantial limitation when applied to the full spectrum of Java to database interaction. They mainly focus on inter-Java application value flows with minimal support to the database frameworks. To the base of our knowledge, no existing work can capture the Java to database value flow statically. The core problem is the interaction involves 3 tightly coupled components. Each of them has diverse and complex behavior. First, the analysis of each component significantly affects the soundness, precision, and scalability of the others. Regarding the diversity and the complexity, the behavior of database framework is complex for current static analysis. It consists of millions of lines of code, and it is highly dynamic with extensive use of reflection, annotation, and branches. And the communication with database is implemented via native code. Due to these factors, general static analysis techniques fail to achieve good, effective soundness, precision, and efficiency. Then the behavior of the database framework is also highly diverse, influenced by many factors. The database API interprets the database access APIs dynamically based on the information collected from the application, such as the API type, entity-to-table mappings, and entity relationships. Based on these informations, the database framework generates and executes a series of SQL statements. This process consists of 4 core steps: new statement, init statement, execute statement, and process result. The behavior of each step is determined by the factors we mentioned above. To keep things simple, we skip the detailed exploration here. You can view the full detail in our paper. Notably, the factors influencing API behavior are also highly diverse. Moreover, SQL is a language distinct from Java, which with a rich syntax and semantics. This further increases the diversity and the complexity of the analysis. To overcome the diversity and complexity, we first propose 2-phase primitive to model the database frameworks and the SQLs. Recall that the database framework handles database access API by generating and executing a series of SQL statements following 4 core steps. The behavior of each step are diverse depending on inputs. For each variant, we define a corresponding framework primitive, capturing its input and output. Similarly, for different SQL operations, we define corresponding SQL primitives to model the behaviors. Based on these primitives, we propose a unified point analysis that integrates the analysis of all components. It includes heap modeling for Java application, database frameworks, and databases, as well as point analysis rules tailored for Java statements, framework primitives, and SQL primitives. Building on these designs, we implement debug, an end-to-end point analysis framework for Java database application. The debug consists of 3 components: the app analyzer, the database framework analyzer, and the database analyzer. They work together to handle the full spectrum interaction and generate a call graph along with a full spectrum point flow graph, which captures the Java to database value flows. The app analyzer integrates the state-of-the-art point analysis techniques for Java application, such as selective context sensitivity. It generates a point flow graph for the Java application code. The framework analyzer and the database analyzer extract information from the application code and the application point flow graph. They transform the database access API calls into a series of 2-phase primitives. By applying tailored point analysis rules to these primitives, debug can generate a full spectral point flow graph for the interaction. So how does debridge perform in practice? We evaluate debridge in 3 perspectives. First, we evaluate its ability to capture Java to database value flows on a micro benchmark called dbmicro and 10 real-world applications. Then we evaluate its ability to identify SQL statements compared to the state of the art. Then we evaluate debridge's utility in client analysis, including 2 security analysis and 1 program understanding task. We first introduce a micro benchmark called dbmicro. dbmicro systematically captures the diverse behaviors involved in Java to database interactions. It consists of 824 test cases and the corresponding ground truths, along with the evaluation scripts. Debridge successfully passed 721 of these test cases, a promising result given the complexity of SQL and database frameworks. Then we apply debridge to construct value flows in 10 popular Java web applications. The experiment result shows that debridge achieves strong soundness, good precision, and high efficiency. Also, it's the first tool capable of constructing such value flows. It still delivers promising results. Then we compare debridge with sLocator, the most advanced open source tool for SQL identification. The experiment result shows that debridge significantly outperforms sLocator in SQL identification. By applying debridge to security analysis, we identify 34 store XSS vulnerability in real-world applications, 30 of which are previously undiscovered. The most of them stem from insufficient input and output sanitization, as illustrated in the earlier example. Additionally, debridge revealed 3 horizontal broken access control vulnerability caused by inadequate access control. For example, in one case, the try block restricts users to get only public data, but the catch block mistakenly allows users to get private data of the other users. In conclusion, in this work, we present debridge, the first end-to-end point analysis framework for Java to database interaction. And we introduce a micro benchmark called dbmicro. It fully captures the diversity involved in the interactions. And we uncovered the 30 store access vulnerability and 3 broken access control vulnerabilities. We built debridge on top of TIE, a state-of-the-art static analysis framework for Java. And we have fully open source debridge and the corresponding micro benchmark dbmicro in our artifact. That concludes my presentation. And thank you for your attention.
Got a question here, yeah. Hi, thanks for your presentation, and I want to ask that, can you compare your approach to the traditional tent analysis? Because since to me, I think they are very similar.
Yes, compared to the traditional tent analysis, they face limitation to the full spectral interaction. They cannot handle the value flow between the database framework and the database. In this work, we model the behavior of the database framework and construct the value flow between the database framework and the SQL precisely. And we model the database framework's behavior by propose a series of framework primitives. Current time analysis cannot understand the behavior of this database framework. Yes.
So I saw in your slide you say introduced a set of primitives to describe the set of framework APIs or the circuit statements.
Yeah.
So what are you exactly describing for? The circuit statements or just the framework APIs?
Wait a minute. As I mentioned above, the framework, the database framework, transform the database access API into a series of SQL statements. The framework primitives model this process, and the SQL primitive models the execution of SQL statement. It describes how the SQL operation influence the points to relation. For example, by these SQL primitives, we model a database statically.
Yeah, I mean, so based on my understanding, you're doing this static analysis over the application called the framework APIs, the ORM APIs.
Yes.
So all you can get is the API information. So how can you just get the information of the whole circuit statement?
Sorry, I didn't understand your questions.
So, I mean, you just said your primitives is to describe the semantics of the circuit statement.
Yes.
But I mean, in static analysis, what you can get is only the API call size.
Yes.
How do you transform the API call size into a set of into a real SQL query?
We model the transformation process. Yes. There is a component called. Wait a minute.
Are you saying that your team did some explicit modeling work for every different database library?
Yes.
Explained how to map it into these operations?
Yes.
Okay.
We're mapping this API to the SQL statement.
Great talk. My name is Min Seok Jung from Korea University, and my question is, you said your tool used selective context sensitivity, right?
Yes.
And my question is whether you used existing selective context sensitivity techniques supported by TIA, or you designed a new one for this work?
We designed a new for this one. First, we model the behavior of the collection, such as array maps, and then we choose to apply deep context sensitive to application code, because the value flow between application code is important for a lot of analysis, such as time analysis. And for other libraries, we apply context insensitive. Yes.
Oh, thank you for.
Let's get the next speaker up here to plug in, please, and we could perhaps fit one more short question if anyone has one. Looking for the next speaker also. Okay, you're sitting right there, great. So we can swap that off. Any last, not super long questions? If not, then we can thank the speaker again. Okay, so next we're going to be hearing from Young He about an approach to correct translation between database queries into different important styles of databases.
Okay, yeah, hi everyone. My name is Yang He from Simon Fraser University. I'm going to present our paper, Graffiti, Bridging Graph and Relational Database Queries. It's a joint work with Rui Jiefang and Ishu Delic from University of Texas at Austin, and Yuepeng Wang from Simon Fraser University as well. Over the past decades, graph databases have become increasingly popular in both industrial and academia due to the flexible data models. Nowadays, we have many graph database management systems, such as Neo4j and Cosmos DB, designed for graph-centric applications like social network and recommendation system. Therefore, many developers migrate relational database applications to the graph databases. However, transition between graph and relational databases requires rich expertise, and writing graph queries that are equivalent to the original SQL query is error-prone. For instance, many Stack Overflow posts reveal that translation between graph and relational queries can be quite challenging due to the misunderstandings of algorithm semantics, joins versus relationships, and other complexities. However, to our best knowledge, there is no prior method to check the correctness of migration, resulting in subtle bug hidden in this post and even the official tutorial. In this work, we propose a method to check equivalence between graph and relational database queries. In a migration setting where developers have refactory relational tables in a graph structure and a relational SQL query in the Cypher language, our goal is to ensure these two queries consistently produce the same results. However, this problem is non-trivial and presents a natural question. What does it mean for two queries to be equivalent? If we don't know the relationship between the data stored in graph and relational databases, then equivalence could be year-defined. This requires us to find a mechanism to align relational and database and graph databases. The solution is to introduce the concept of a user-provided transformer, which is inspired by schema mapping from the database community. It specifies data equivalence between graph and relational databases, and thereby enable us to define query equivalence. Using user-provided transformer as specifications sounds good, but how to specify these transformers? The insight is that we can naturally specify transformers via data log rules. Even though graph databases don't have explicit relations, we can think of each node and edge type as a relation. To make this concept more concrete, let's consider a user-provided transformer example in practice. Here, we have a graph database where employee and department nodes are connected via work edge. Specifically, it indicates that both Alice and Bob work in the IT department. In contrast, the relational database only has two tables, employees and departments, with a foreign key DID to maintain the relationship. It also indicates that Alice and Bob work in the IT department. To ensure these two databases maintain the same data, we use a user-provided transformer to align their structures and semantics. Take the work edge as an example. This rule specifies that for each path from employee to department through a work edge, there is a corresponding rule in the employees table. Now that we have a way of specifying data correspondence, we can formally define equivalence as follows. Let Q be a graph query of a graph schema S, and Q prime be a SQL query of a relational schema S prime. These queries are equivalent modulo a user-provided transformer T, if and only if. For any graph instance of the graph schema S and the relational instance of the relational schema S prime that satisfies the transformer T, executing the two queries on this instance generates the same results. Since this formal definition is a bit abstract to understand, I will explain it in more detail. Suppose that we have an arbitrary graph database and a relational database that satisfy a user-provided transformer. A graph query produces a tabular result when executed on the graph database. Meanwhile, a relational query returns another table when operated on the relational database. If these two resulting tables from both queries are identical, then these two queries are considered equivalent. Now, we have an equivalent definition between graph and relational queries. But how can we check it? A strawman idea is to simply encode query semantics in SMT and directly check the definition. However, checking equivalence in this way may present a problem. We need an SMT encoding that can simultaneously describe graph and tabular data. Unfortunately, from our preliminary experience, such an SMT encoding doesn't work well in this verification task. To solve this issue, we reduced the original problem to CQ equivalence checking using a correct by construction transpilation technique. Concurrently, we first transpile the graph query into a relational query, and then leverage the existing method to check equivalence of two relational queries. If we can automatically transpile graph queries into relational queries, why do we need to verify equivalence between these two relational queries? The reason is that a graph schema only can be transpiled to some relational schema, but it may differ from the target relational schema. More specifically, let's consider this example. Given these two schemas, it's difficult to transpile a graph query over this graph schema to a relational query over this target relational schema. Instead, generating a relational query over a relational schema that has three tables corresponding to this graph schema is more straightforward. Therefore, the first insight is that transpile a graph database into a relational database of a certain shape is easy. We capture this shape using the notion of a standard transformer, which directly maps nodes and edges to relational tables with the same attributes. Additionally, graph queries can be translated to relational queries over these new relational tables. The second insight is that transpilation reduces the original problem into an easier CQ equivalence checking problem over different schemas. This area has been well studied, and we have many tools can check equivalence by verification or falsification. More concretely, here is how our method works. The original verification task aims to verify equivalence between graph and relational queries. Since this direct verification problem is challenging, we reduce to a well-studied problem, CQ equivalence checking. Our method first derives a so-called standard transformer to convert the graph database into an induced relational database. Then, it applies a correct by construction transpilation technique to generate a transpile relational query that is provably equivalent to the original graph query modulo this standard transformer. Based on these two transformers, we can construct a residue transformer to ensure data equivalence between the induced and the target relational databases. And it also serves as a specification for the subsequent verification process. Finally, an off-the-shelf CQ equivalence checker can be used to check equivalence for these two relational queries. Now, let's walk through an example to better understand how our method works. Suppose we have a graph query over this graph schema, and a relational query over this relational schema, and a user-provided transformer to align these two schemas. These two queries are equivalent modulo this user-provided transformer. The answer is yes. And I will show you how our methodology proves this. Our method first automatically derives a standard transformer. It's basically a set of rules to convert nodes and edges into relational tables where attributes become columns. Consider this a standard transformer, By applying to previous graph database, we can construct 3 induced tables corresponding to the nodes and edges in the graph. In general, standard transformer converts any graph database into a rational one, which means our method can check equivalence for queries that conform to arbitrary schemas. Next, we transpile the original graph query into a equivalent rational query, module this standard transformer. Based on the standard transformers, we define correct by construction transpilation rules and prove them correct in our paper. I want to explain how translation works. Please refer to our paper for more detail. For this example, transpilation will produce a transpiled rational query that is provably equivalent to this graph query modulo the standard transformers. Before checking the CQ equivalence, we must construct residue transformer to align the induced and targeted rational databases. Recall that residue transformer describes data equivalence between 2 rational databases and serves as a specification for the CQ equivalence checking. And we can automatically infer a residue transformer from user-provided transformer and a standard transformer. For example, the rule from the user-provided transformer preserve the same relationship between the work edge and the employees table. And the rule from the standard transformer ensure data equivalence between the work edge and the work prime table. Then we can infer a residue rule that preserve the consistent relationship between the work prime and the employees table. Similarly, we can derive other rules for the remaining table in the induced rational database, namely employee prime and department prime. Conceptually, residue transformer tells the CQ equivalence checker how to align two rational databases over different schemas. With all this component in place, we finally can check equivalence for these 2 rational queries. Using existing CQ equivalence checker, we can prove this transpiled rational query is equivalent to this target rational query modulo the residue transformer. That's to say, the original graph rational query pair is equivalent modulo the user-provided transformer. This is the whole verification process about this work. Now, let's focus on the evaluation part. We implement a tool called Graffiti and instantiates with 2 existing CQ checkers. The first one is a bounded model checker called VerEco proposed in 2024. It reviews equivalence by generating count examples and produces no false positives. The second checker is a deductive verifier named Mediator proposed in Popo 18. It proves equivalence for CQ applications and produces no false negatives. In this work, we explore 2 research questions. Can these instantiations of Graffiti find bugs and verify equivalence? We evaluate Graffiti on about 400 equivalence verification tasks between Cypher and CQ queries. These tasks are sourced from Stack Overflow posts, online tutorials, prior literature, and GPT translations. When using VerEco as a backend, we can check equivalence for all benchmarks. Among them, 376 are proved equivalent with an average bound of about 20, and only 34 are refuted with count examples in an average revision time of 23.4 seconds. We mainly inspected all these count examples by executing them on MySQL and Neo4j databases and confirmed that they were all valid and can produce different results. This demonstrates that Graffiti can identify subtle bugs in a short time. The main takeaway from this experience is that using a bounded model checking backend, Graffiti can identify 34 bugs. When using Mediator as a backend, we only support less than half of benchmarks. Among this supported pair, we can prove 152 are equivalents, which are also confirmed by bounded model checking. Mediator return unknowns for the remaining benchmarks because it needs to find a complex invariant for long join chain, which leads to expensive SMT queries and thereby triggers timeouts. The average running time for these verification tasks is about 70 seconds. The takeaway that using a deductive verifier, Graffiti can prove equivalence between about 80% of supported benchmarks. Overall, in this work, we propose Graffiti, the first technique for reasoning about equivalence between graph and rational queries, modulo use provided transformers. This is the end of this talk. Thanks for attention.
Let's see. Let's start with the person who didn't ask previously. Yeah.
Hello, Amir from Edinburgh. Very nice presentation. I was wondering to what extent the features of the Cypher language you're supporting. In particular, do you support variable length path or optional match?
Okay, yeah. We might extend our Cypher query for variable length pattern matching, and it can be implemented with recursion expressions. Okay, yeah. As for the option match, we already considered it.
Okay, yeah. In particular for the variable length path, so you need to support recursion in SQL. That makes the equivalence of SQL queries very complicated. Do you have any thoughts?
Yeah, true.
That? Okay, thank you.
Thank you.
Hi, thanks for your presentation. And I want to ask that, is it hard for a user to write the transformer because when the graph database becoming more complex, I think maybe it's harder.
Maybe, yeah. Say the average transformer size consists of about 6 rules, and from our experience, writing a transformer for a benchmark maybe cost 1 minute. I think it's acceptable.
So the transformer size is linear to the complexity of the graph schema, or it's fixed?
No. Yeah. It depends on the graph and the rational schemas, because you need to write a rule to describe how you map a data correspondence between this graph and the tables.
Yeah. So have you done any user study, like?
No. Oh. Yeah. Maybe we can do it in the future.
Oh, thanks.
Yeah.
Thank you for the talk. So it's known that the graph model is an instance of the rational model. So it's nice to see that you can do this equivalence checking between different models. So one question I'm curious is actually about what kind of real-world use cases you can think of, because it does not seem like I don't know many projects that switch from one model to another. It's more like, when you start a new project, you pick maybe a more novel data model. So do you see are there projects in real world that does this switch?
Let me think. I think there's a project called Apache Edge. They use a graph API to manipulate rational databases. Maybe you can check it.
Yeah. I see. Maybe a related comment is, I think there's some graph databases that provide the graph query, but they're implemented using the relational databases. Maybe there's another way where you can have a relational database where you accept relational queries that are translated to graph queries.
Yeah. Thank you.
And why don't you go plug in while we close things out here? Any last audience questions? Let me try to fit in one of mine. Is it the case that you're only supporting non-recursive data log programs in transformers?
Yeah. Right now we don't support that.
Got it. Okay. Makes sense. Okay, let's thank the speaker again. So final talk of the session is on a better test oracle for database isolation by Lasse Moldrup. And 3 seconds left, and go.
Okay, thank you for that introduction. And today I'll be introducing Audit, which is 3 algorithms that significantly improve on the performance of the state-of-the-art in testing of weak database isolation. And to start off, I would like to give a motivating example to explain some of those words. So consider a chat room where we have Alice, Bob, and Charlie communicating over a database. Say that Alice poses a question and Bob answers the question. Now Charlie would be very confused if he received the answer before the question. So one way to think of what went wrong here is that the question in some way caused the answer, so therefore Charlie should view the question before the answer. And this property is in general called causal consistency, and it's a guarantee provided by databases to its clients. However, notice that concurrent writes can appear in any order to readers. And in that sense, it's a weaker database. It's a weaker guarantee. For instance, if you had 2 simultaneous questions, 2 people could see them in different orders. So you might be wondering, why do we care about these weak guarantees? Why shouldn't the database just provide the strongest possible guarantees to all of its users? Well, there are a few reasons. One of them is performance. So the database can provide higher throughput if it also provides weaker guarantees. And the one is fault tolerance, where with strong isolation guarantees, the database can simply shut down or not be able to respond to requests in the case of network faults. And finally, we also care about it because it's often the default in real databases to have weaker guarantees. Okay, but there are some problems, which is one of them is that databases have repeatedly been shown not to actually satisfy the guarantees that they say they will give. Or they just provide simple pros as guarantees. And another reason for this is that databases are actually really complicated distributed systems. For instance, what you might think of as a single database could actually be 5 databases in a trench code communicating over the internet. And therefore, we need some way to find these errors. And one solution is black box testing, which is what I'll be introducing today. So to explain this, we need some concepts from the theory of database testing. So when we look at an interaction where some clients send some data to the database, we call this interaction a history. And so you can see we have here 3 clients that are interacting with the database, and each client is sending what are called transactions here. So you can think of transaction, if you're not familiar with the database theory, as, for instance, in a bank where you want to move some money from one account to another account. And these transactions consist of operations, which in this setting are just simple reads and writes to values such as x and y. And finally, these transactions are ordered on sessions based on each client. And now we can formally define these guarantees that I mentioned earlier as isolation levels. So formally, an isolation level is a predicate on history. So you can think of an isolation level as a function, takes in a history, and then says, is this history satisfied? And some examples here are causal consistency, which I already mentioned, read committed, which is actually even weaker than causal consistency and often the default. And then serializability, which basically says that you can view all the transactions in some order that makes sense. And this is usually what developers think the database is doing, but not what it's actually doing. Okay, so if we then want to test a database or a cluster of databases, well, we start with a database and some isolation level that we want to test it for. Then somehow we generate a bunch of transactions, some reads and writes, and send it to the database. Then we can look at what we get back from the database and collect it into one of these histories. And the final step is then to check if the history satisfies the claimed isolation level. Okay, so this leaves some questions. For instance, how do we check if a history satisfies a given isolation level? And also, maybe these bugs are very rare, so we need to maybe check very big histories or run on very many histories. And this motivates the need for very efficient consistency checking algorithms, which is what the problem is called of testing whether a history satisfies an isolation level. Okay, so I'll go over some brief relevant literature here. In the 70s, Papadimitriou showed that checking whether a history satisfies serializability is NP-complete. This is a bit of a bummer if you want to do this at scale. But then, skipping over a bunch of important research, in 2019, Biswas and Inier showed that these three isolation levels of read committed, reatomic, and causal consistency, abbreviated as RC, RA, and CC, are checkable in polynomial time. And then last year, Liu et al. Proposed Plume, which provide efficient algorithms for these three isolation levels that are significantly improve the state of the art in terms of real-world performance. However, if you look at the complexity, it's something like a number of transactions cubed times some other factors. And so this leaves us with some questions, like how fast can we truly test these weak isolation levels in theory and in practice? So this is where our work Audit comes in, which is three algorithms for RC, RA, and CC. And you can see for RC and RA, we run in n times square root n time for n operations. And for causal consistency, we run in n times k time for k sessions. And typically, the number of sessions is small in practice. So this is obviously a big theoretical improvement over the state of the art. But you might be thinking, n times square root n, that sounds a bit strange. Are you sure that's not a linear algorithm, for instance? And here we prove that Audit is actually essentially optimal by showing lower bounds for these three problems. We show that under some assumptions, no algorithm can do better than n square root n. But in fact, our lower bounds are not just restricted to these three problems. In fact, any isolation level that is stronger than read committed and weaker than causal consistency, this lower bound applies to. Okay, so in order to give some ideas on how we did this, we need a different view of histories. So it has long been noted that you can view histories as graphs in the following way. So we have a history here on the left with two transactions that write to X, and then another transaction reading those writes in the opposite order. Okay, so we can turn this into a graph in the following way. We add a few different kinds of edges. So on the left, you can see we have an edge labeled SO, which stands for session order. And it simply orders T1 and T2 because they're on the same session. Then we also have some blue edges called WR, which stands for write read. And those simply relate writes with the reads that read them. And finally, we have on the right the program order, which simply relates operations within the same transaction. Now, so once we have this view of histories, we can give a different formalization of isolation levels, which was also introduced by this paper in 2019. So they basically show that if you have your favorite isolation level I, then you can define it in the following way. Take some history H, and then you say this history H is consistent if I can find some total ordering of all the transactions. So you can see in the picture here we have all of the transactions in the history in some order, such that the write, read, and session order edges follow this ordering. And then there are also some constraints that are dependent on the specific isolation level. So I will give the example of read committed here, and bear with me here because this gets a little bit technical, but I'll give an example afterwards. So the rule for read committed says that when you have a transaction T3 that first reads some transaction T2, and then later reads X from a transaction T1, where T2 also writes to that key X, then T2 should come before T1 in the commit order. So just to reiterate, this is an implication that whenever you have the pattern on the left in your graph, then T2 should come before T1. And I promised an example, so here it is. We use the same history from before. And if you squint, you can see that the two pictures on the left and the right are actually basically the same. In fact, if we just visually swap T1 and T2, you can see that it's actually exactly the same. So therefore, the definition tells us that T2 should be in the commit order before T1. However, remember that the commit order also has to agree with the session order. And so therefore, this cycle between T1 and T2 is actually a witness of inconsistency with read committed. And this also serves as a basis of Audit, where the algorithm is essentially finding triples T1, T2, and T3, like on the right here, and then remembering in a partial commit order that we call CO prime, that T2 should come before T1. And then if those those inferred edges form a cycle, then we know that the history is inconsistent. Okay, but even if you could enumerate all these patterns on the right as efficiently as possible, there could still be a cubic number of them, which would lead you to a cubic algorithm. So we have to find some clever ideas. So one of the ideas that allows audit to achieve the complexity that it does is that we don't actually have to enumerate all of the triples. And I'll explain that with an example. So consider the history on the left here. We have 3 transactions writing to X, and then another transaction reading them in that same order. Okay, so we can apply our rule from the right and see that T1 should come before T2. We can do it again for T2 and T3. But actually, since the program order is transitive, we can also do it between T1 and T3. But remember that we were only interested in finding cycles. So here it is actually not necessary to infer this edge because we already have a path from T1 to T3. And so this is one of the mechanisms for how audit achieves the complexity that it does by simply not enumerating cases like this. And in fact, it only enumerates O of n square root n of these triples. Okay, so we implemented audit in Rust and ran some experiments. We tested it on 3 real-world databases using standard workloads. So those are scripts for generating reads and writes to the database from the literature. And then we ran it on 2 to the 10 and 2 to the 20 transactions, which correspond to at most 50 million operations. Okay, so we compare it to Plume, which is the current state of the art. And as you can see here, we have a graph with the running time of audit on the x-axis and the running time of Plume on the y-axis. And so you can see that the middle diagonal line, if the points are above that line, then audit was faster. And this is also a logarithmic plot. So each successive line means a factor of 10 improvement over the state of the art. So just to drive the point home, in this section we have 100 to 1,000 times speed up over the state of the art. And the picture repeats mostly for the read atomic and causal consistency levels. And you can see the numbers here as well, where we achieve on the 20% largest histories speedups of around 240, 260 times speedups. Okay, so in conclusion, we have argued that we need efficient algorithms for this problem of testing weak isolation, and that audit is not only achieve this quickly in practice, but also does it so optimally in theory. And finally, the lower bounds that we use are general in the sense that they apply not only to these 3 isolation levels, but to any isolation level that you can fit in this range. And as a final remark, me and my co-author hope that more people in the PL community can use tools such as this to prove lower bounds for more problems. Thank you for your attention.
Any audience questions here? I can start with one then. So the technique you presented here lets us run a single test. Do you have any kind of principled guidance for constructing test suites that would tend to be sufficient for catching bugs?
So that's kind of outside the scope of what we are doing. We are mostly just, in this work, focused on improving the efficiency, but there are other works that do this kind of thing. Also try to run the databases in a way where they inject faults to try to provoke errors and this kind of thing.
Got it. Okay, thank you. Anyone inspired with a question in the last 30 seconds? I can try another one then. If we're using optimistic concurrency control and we might be rolling back transactions when we notice issues, does that create any interesting twists for the kind of thing you're doing here?
Not really, because we're just looking at the committed transactions mostly here, because I mean, it's pretty easy to tell, like if you read an aborted transaction or something, that's very easy to check for. So the interesting part really happens with the committed transactions.
Got it. Thanks.
I was wondering if any of the tests that you did, you also found some violations?
Yeah, so I actually have a bonus slide for this. So the answer is maybe, because well, we did find some histories that have violations, but we're not 100% sure that they're like bugs in the database, because like the pipeline from the database to us having a history that we can test on is quite complicated, and we're not sure if the errors maybe came in that process.
So these databases don't provide their own logging?
Okay, what do you mean by that?
So I would imagine the pipeline would be take the database, bombard it with some transactions, and then make the database, force the database to log some transactions.
Yeah, so we're not actually forcing the database to log transactions.
Okay.
We're like acting as a client, or well, we're actually using someone else's work for this, but they're using the database as a client and then logging what the client sees, basically.
Okay. So then what could go wrong in this pipeline?
Yeah, that's a good question. We haven't really thought that deeply about it, but...
So anyway, my question was about, if you find a violation, can you also pinpoint to the developer that here is where you might want to fix?
Yeah, so the tool will spit out as best as it can, like where in the history the bug happened. So it'll give you some transaction and say these transactions are wrong somehow. So you can use that to debug the database.
Okay, thanks.
Any other audience questions? Let me go for one more of mine then. So you presented this just in terms of read and write operations on some universe of objects. How do declarative queries look in this kind of setting?
So I have to say I'm not familiar with that term.
Oh, I just mean like Postgres lets you run a complex select query that could be touching all kinds of objects and use interesting logic to decide which ones are going to be touched.
Yeah. Well, so that's an interesting question, and well, I guess here we're just interested in finding bugs, so we sort of use the easiest thing possible, and this is what people have done for many years now. But there are some new research into trying to test like more complex queries as well.
And I'm thinking about implementation techniques like predicate locks, which would, I think, go with a stronger consistency level than you're dealing with here, but maybe there are similar techniques that are used for the weaker levels.
Yeah, so I mean, this kind of thing is like an open area of research, I guess. Yeah.
Okay, thanks. Going once, going twice. Okay, let's thank the speaker again. I think that's a wrap for this session and for the conference. Thanks everyone for coming.